Welcome back to the deep dive. Today, we are really setting aside the general summaries. We're going deep, like really deep into advanced optimization theory.
Hmm.
We are talking about problems that are, well, so complex that your standard convergence guarantees, they just melt away.
That's absolutely right. We're going to dissect really symbol by symbol a pretty dense but I think quite beautiful paper. It's called A First-Order Method for Constrained Non-Convex Non-Concave Minimax Problems Under a Local Kurdyka-Łojasiewicz Condition.
Okay, quite a mouthful.
It is.
And look, we know you, our listener, you follow this field. So our mission today isn't to, hold your hand through the absolute basics. It's more about synthesizing the genuinely novel insights here.
Right. We want to turn this highly technical paper into something like a conversational blueprint.
Exactly. Aiming for an exhaustive, like you said, symbol by symbol understanding of why their specific solution works and, crucially, what it might mean for your own algorithmic design work.
Okay, so let's start with the definition of the beast they're tackling here. We're in the world of minimax optimization.
Right, the kind of stuff that pops up everywhere, robust control, GNs.
Exactly. Generative adversarial networks, reinforcement learning, distributionally robust optimization, you name it. But here it's complicated. Really complicated by two main factors.
Okay, what are they?
First, non-convexity. The objective function is non-convex in the variable we're minimizing, that's x, and it's non-concave in the variable we're maximizing, per king. So no easy saddle points necessarily.
Right, the landscape is messy. And the second factor?
The second factor is tough constraints, specifically on that inner maximization problem.
Okay, so the inner problem, where player Y is trying to maximize the objective, that player isn't free to roam.
Not at all. They're restricted by a constraint set defined by C hui less than or equal to 0. And this C function is smooth, but it could itself be non-convex.
Okay, and that constrained inner maximization, that's the real source of difficulty compared to standard minimax, right? That's where classical approaches often break down.
That's precisely it. Handling those constraints rigorously is the core challenge. So to manage this constrained complexity, they introduce a really fascinating theoretical tool. They call it the lifted minimax problem.
Lifted. What does that mean in practice?
Well, essentially, it involves introducing an auxiliary variable, let's call it z for now. By adding this variable, they effectively reformulate the original constraint problem into a higher dimensional space.
Okay, why do that? Does it simplify things?
In a structural sense, yes. The idea is that in this higher dimensional lifted space, the structure of the problem, particularly around the constraints, becomes more, let's say, transparent and easier to analyze.
Okay, interesting. So you lift it up to see it better.
Sort of, yeah. And here's the theoretical linchpin, the real key insight. They don't assume the entire problem has perfect structure, like global convexity or anything like that.
No, that would be too strong for these kinds of problems.
Way too strong. Instead, they only assume that the inner problem of this lifted version satisfies a local Kurdyka-Łojasiewicz condition. Usually we just call it the KL condition.
Okay, the KL condition. We'll definitely need to unpack that. But the key word there is local.
Absolutely crucial. It's not a global assumption. It only needs to hold near potential solutions. Think of this local KL assumption as like finding a hidden structure within the chaos, but only where it counts.
And if they can show that this local property holds for the lifted problem, what's the payoff?
The huge theoretical payoff, the thing that makes the whole approach work, is that the resulting maximal function, that's the value you get out of the inner maximization problem, is guaranteed to have a specific property. It's called a local holder smoothness property.
Holder smoothness. Okay, not standard Lipschitz smoothness, but something related.
Exactly. It's a slightly weaker form of smoothness, but it's enough. This holder smoothness is the critical link that connects the structure of the inner problem via KL to the behavior of the outer problem.
Got it. So local KL on the lifted inner problem gives us local holder smoothness on the function we're trying to minimize overall.
Precisely. And the algorithm they build on this foundation is, well, it's a kind of hybrid architecture. It combines two main components.
Okay, what are they?
First, they use a sequential convex programming method, or SCP, to handle that difficult constrained inner maximization.
SCP, so solving a sequence of easier convex problems to approximate the hard non-convex one.
That's the idea. And this SCP method is nested inside an inexact proximal gradient method, or IPG, which tackles the outer minimization problem.
Inexact, meaning we don't need to solve the inner SCP part perfectly at each step.
Exactly. We only need an approximate solution from the inner loop, which makes the whole thing computationally feasible.
And the combination of these two what does it ultimately give us?
It gives them something incredibly valuable in non-convex optimization: complexity guarantees.
Ah, okay. Not just it converges eventually, but how fast it converges.
Right. They establish a rigorous, finite time bound on how many iterations you need to find an approximate stationary point. And we'll see that this bound scales predictably. It depends directly on the parameters of that local KL condition, the exponent theta, and another parameter sigma.
Okay, fantastic. So we have a clear path. Let's unpack this systematically. We need to start with the foundational notation. Really nail down the problem setup.
Yep, define the problems, the notation, the core assumptions.
Then we'll move into the theoretical properties, digging deep into that KL condition, and especially that crucial Holder smoothness result.
And finally, we walk through the two linked algorithms, SCP for the inner loop, IPG for the outer loop, and understand how their complexity guarantees are derived.
Sounds like a plan. Let's dive into section 1, problem definition and foundation.
Okay, so the primary focus, the main problem they want to solve, is labeled as problem 1 in the paper. Let's maybe vocalize the structure first.
Okay. So looking at 1, we see it's a minimization over X, maximization over Y.
Max over Y. So a classic minimax structure.
But crucially, that inner maximization over Y isn't unconstrained. There's a subscript. CY less than or equal to 0.
Exactly. CY equals 0. This is the set of constraints that the Y player must satisfy, and the function C itself could be non-convex, mapping Y to potentially multiple constraint values.
Okay. And inside the objective function, the thing being minimize, maximize, we have 3 terms.
Right, there's fxy. This is the main interaction term, the core function. And critically, this f is assumed to be smooth, but potentially non-convex in x and non-concave in y. This is where the main non-convex-nonconcave nature of the problem lies.
So that's the complicated part. What about the other 2 terms?
Px and
Good. Then you have plus px and ky. These functions, p and q, are assumed to be, let's say, simpler. They are proper, closed, and convex functions.
Convex, okay, so they add some nice structure. What kind of functions are we talking about typically? Think of them as regularization terms, maybe, or indicator functions for simple sets. For example, px could be an L1 norm penalty on x to encourage sparsity, or ky could be an indicator function that restricts y to lie within a simple box or ball, in addition to the CY constraints.
And the key is that they are simple in the sense that we can easily compute their proximal operators. That's usually what simple means in this context.
Precisely.
Yeah.
They are chosen to be prox-friendly, which is essential for the algorithms later, particularly the proximal gradient method.
Okay, so that's problem 1, the core focus. Smooth F, non-convex-nonconcave, simple convex P and Q, and that difficult smooth constraint CY on the inner maximization.
Exactly. Now, they also introduced problem 2. This looks like a more general form. It's minimization over x, subject to some constraints, dx, igios, 0, of a maximization over y is subject to cy of just fxy.
Right, so here both x and y have explicit constraints, and the simple p and q terms seem to be folded into f, or the constraints. Why define this problem 2 if they spend all their effort analyzing problem 1?
It's a standard technique, really. They're showing how the slightly more general problem 2, where the outer variable x also has constraints, can be reduced to solving a sequence of problems that look like problem 1.
How do they do that reduction?
They use a penalty approach for the outer constraints, dx equals 0.
Okay, the classic penalty method. So instead of strictly enforcing dx equals 0,
you move it into the objective function. You add a penalty term that becomes very large if the constraint is violated.
Right, so you add something like a penalty parameter times the violation amount.
Exactly. They add a term, rho times the squared Euclidean norm of the positive part of dx.
The positive part, you mean dx if dx is positive and 0 otherwise.
Precisely. They use the notation u plus, which means max, u0, applied element-wise if dx is a vector. This ensures a penalty only kicks in when djx0 for some component j.
And rho is the penalty parameter.
Yes, and the key is that you create a sequence of problems where you let rho tend to infinity. As rho gets larger and larger, the solutions to these penalized problems are forced to satisfy the original constraint dx equals 0 more and more accurately.
Okay, so solving the sequence of penalized problems, each of which looks like problem 1, with the penalty term absorbed into px essentially, allows you to approximate the solution to the more general problem 2.
That's the idea. It allows them to focus all the heavy theoretical machinery on handling the inner constraint cy in problem 1, knowing that outer constraints dx equals 0 can be dealt with using this standard penalty framework.
Clever. It isolates the main difficulty.
And just for context, they briefly mention problem 3, which is the simpler, fully unconstrained case. Just makes max C fx y plus ax COA.
dx. No CO0.
Exactly. And they note that most of the prior work, especially in areas like JANS, adversarial training, reinforcement learning, focus on this unconstrained or maybe box-constrained setting. People made assumptions like a global Polyaklos-Evasic PL condition or looked for weak, minty variational inequality solutions.
So the big gap this paper addresses is specifically adding that non-trivial functional constraint CUI to the inner maximization. That's the key novelty.
That's the core contribution, yes. Handling that constraint requires more advanced tools from non-smooth analysis, hashtag 1.2 notation, terminology, and assumptions.
Okay, so let's get into those tools. Notation first. They use pretty standard stuff for inner products, norms, angle brackets for inner products, standard Euclidean norm unless specified, like L1 or L infinity.
Right. U, V for the line segment, dis S for the distance from point X to set S, delta S for the indicator function, 0 if in S, infinity otherwise. All fairly standard.
But then we get into the non-smooth stuff, cones. They define NSX and NSX.
Yeah. So NSX is the regular normal cone, sometimes called the prenormal cone. If NS was a nice convex set, this would essentially be the set of vectors that form an angle of 90 degrees or more with all vectors pointing from X into S. Think outward pointing normals.
Okay, but our set S, defined by Cy at y equals 0, where C might be non-convex, might not be nice and convex.
Exactly. It could have weird corners or boundaries. So for non-convex sets, the regular normal cone can be too small. It might even be empty at important points. That's why we need the limiting normal cone, NSX.
And how is that defined? It sounds like a limit.
It is. You define it via sequences. You look at points xk that converge to x within the set S, and you look at vectors vk, where each vk is in the regular normal cone at xk. If these vk vectors converge to some vector v, then v belongs to the limiting normal cone nsx at x.
Ah, okay. So it's a more robust definition that captures the geometry, even at bad boundary points, by looking at the limits of normals from good nearby points.
Precisely. It's essential for formulating necessary optimality conditions, like KKT conditions, for non-smooth, non-convex problems. Without the limiting cone, the theory just doesn't work reliably.
Got it. Okay, cone handled. Now, smoothness. We know standard Lipschitz continuity. The function value doesn't change too quickly.
Right, bounded rate of change. And standard Lipschitz smoothness, often just called smoothness, refers to the gradient, L and blah, S1y. The gradient doesn't change too quickly, which implies bounded curvature.
Okay, standard stuff. But you mentioned the key concept here is Holder smoothness. How is that defined again?
So a function f is Holder smooth if its gradient satisfies Kalev's fy, Lsy, sy2. Here L is the Holder constant, and nu, written as the Holder exponent, which must be in the interval $2.11.
Okay, so the difference in gradients is bounded not by the distance xy, but by the distance raised to the power nu.
Exactly.
What's the intuition if nu is less than 1? Let's say nu is 0.5.
If nobla f excess 5, then nobla fy is bounded by L times the square root of xy. Since the square root function grows slower than the identity function near 0, this means the gradient can change more rapidly for small changes in x compared to a standard Lipschitz smooth function, where...
More rapidly, so less smooth.
Kinda, yes.
Yeah.
It's less smooth than Lipschitz smoothness, but it's still a controlled type of non-smoothness. The function's surface might be more rugged or sharply curved than a standard smooth function, but the rate of change of the gradient is still bounded by this specific power law, x and u.
And you mentioned this is crucial because it's derived from the KL property later.
That's the key connection we'll see in Theorem 1. The KL exponent theta of the inner problem will directly determine the Holder exponent nu of the maximal function f. Okay, since our overall objective function p psi x plus px involves the potentially non-smooth maximal function f and the non-smooth but convex px, we can't just use gradients to talk about optimality. We need subdifferentials.
Right. Enter the world of generalized derivatives. They start with the regular subdifferential denoted partial phi q. How is that defined?
It's defined using a limit superior condition. A vector v is in the regular subdifferential of phi at x if essentially the first order approximation phi x plus phi yx doesn't overestimate phi q much as y approaches x. Formally, lim sub px yx phi y x y x 0.
Okay, so it's the set of vectors v that define supporting hyperplanes, at least locally from above.
That's a good intuition. But Just like the regular normal cone, the regular subdifferential can be too small or empty for non-convex functions at certain points.
So we need the limiting version again.
Exactly. We need the limiting subdifferential, denoted partial.
Okay.
Again, it's defined via sequences.
Let me guess. We take sequences xk converging to x, find regular subgradients vk at xk, and if vk converges to v, then v is in the limiting subdifferential.
Almost. There's one extra crucial condition. The sequence xk must converge to x in a way that the function values also converge. Phis must converge to phix. They use the special notation xk dual fig x to denote this type of convergence, sk dual fix and fixk.
Ah, okay. So v is in partial fix if there exists a sequence xk such that xk x right terminal fix and a corresponding sequence vk in partial hat k such that vkb.
Precisely. That x right terminal condition is vital. It prevents weird behavior if the function phi has jumps or inconsistencies near x. It ensures we're only considering sequences where the function behaves reasonably well.
And why is this limiting subdifferential the preferred tool?
Because it has the nice properties we need. If phi happens to be continuously differentiable, partial fix just contains the gradient nabla fix. If phi is convex, partial fix coincides with the classical subdifferential from convex analysis. And importantly, it obeys calculus rules, like the sum rule under certain conditions.
Like the sum rule mentioned, partial phi1 plus phi2 x plus partial phi2 x plus phi1 is smooth, and phi2 is just lower semi-continuous.
Exactly. That rule is fundamental for analyzing our objective phi x plus px, assuming we can show f is smooth enough or handle its subdifferential.
Okay, subdifferentials defined. Now what about these slopes? They define one nabla phi in Formula 4 and another nabla phi in Formula 5. Wait, same notation.
Yeah, that's a bit confusing in the text. Formula 4 defines the slope, sometimes called the Fresh-S slope. It's defined as the lim sup of phi x y as y approaches x. It measures the steepest rate of decrease locally.
Okay, steepest descent rate.
But the more useful one, the one that connects directly to the limiting subdifferential, is defined in Formula 5. This should probably be called the limiting slope. It's defined as the limit of the slope nabla phi as y converges to x in that special x-right r phi sense.
So the limiting slope is the limit infimum of the regular slopes nearby, considering only well-behaved sequences.
Exactly. And the crucial connection, the reason we care about the limiting slope, is that it equals the distance from the zero vector to the limiting subdifferential. Nabla phi x equals 0, partial phi.
Okay, that's the key takeaway. The limiting slope is our practical numerical measure of non-stationarity. If the limiting slope is 0, it means 0 is in the limiting subdifferential, which is our condition for stationarity in non-smooth optimization.
Precisely. If the limiting slope is positive, it tells us how far we are from being stationary and implicitly the potential for descent. Hashtag tag 1.4 stationary points and problem setup.
So this naturally leads to their definition of success. Definition 1, the epsilon, stationary point. Since finding a point where the limiting slope is exactly 0 is often impossible computationally.
We aim for an approximate solution. First, they define a set, epsilon. This is the set of all points x in the domain of phi, where the limiting slope, nabla phi, or equivalently, this domain partial phi, is less than or equal to some small tolerance epsilon.
Okay, so epsilon is the set of good enough points, the points that are genuinely epsilon stationary.
Right. Now, an epsilon r stationary point x doesn't necessarily have to be in epsilon. It only needs to be close to it. Specifically, the distance from x to the set's epsilon must be less than or equal to r.
So dist x epsilon equals r. Why this extra r tolerance? Why not just aim for a point in epsilon?
It's a practical concession often needed in non-convex optimization algorithms. Sometimes the algorithm might oscillate or chatter near the truly stationary region's epsilon without ever landing exactly inside it. This definition says, okay, if you get within distance r of that good region, we'll count it as success. The radius r itself often depends on epsilon too, as we'll see.
Got it. It's a slightly relaxed but computationally achievable target. Okay, let's nail down the core functions and sets using their notation from 6 through 9.
Right, so x is the domain of py is the domain of q. We assume y is compact, which is important. dy is the diameter of y. mq is related to the bounded variation of q on y.
And S is the feasible set for the inner maximization.
Yes, S is the intersection of y, the domain of q, and the set yc, y0. So y has to be in the domain of q, a, and d, satisfy the explicit constraints.
Okay, now the functions, fxy is defined in 8. It's fxy/qy, and then minus the indicator function delta c.
Y. So SXY encapsulates the entire objective for the inner maximization, including making it minus infinity if the constraint CY00 is violated.
But fx in 9 is the maximal function. It's simply maxi fxy. This is the value of the inner problem for a fixed x.
Since fx is the function we really care about understanding the properties of, like its smoothness.
And finally, the overall objective function we want to minimize is phi x. Also in 9, it's phi xx plus px.
Yep. So our goal is to find an epsilon r stationary point of this potentially non-smooth, non-convex function px. And chi is just the minimum value makes px. Hashtag 1.5, the lifted minimax problem, and local KL.
Okay, now we arrive at that technical centerpiece you mentioned earlier, the lifted problem, defined in 10. Let's look at this. Minimize over x, maximize over yz, subject to bark, yz, is of f. Wait, the objective looks almost the same. fxy plus pxqy. What happened to z in the objective?
It's implicitly there through the constraint and the domain. The full objective in the lifted intermax is fxy, qy, and that delta y term ensures z stays in the domain of q. But the main action is in the constraint bark, yz equal.
Right, let's look at that surrogate constraint bark yz defined in 11. It's defined component-wise for each constraint j. Bar jyz is cjz, okay? The original constraint evaluated at z.
Plus a linear term, the inner product of the gradient NOLA cjz with the difference y.
So a first-order Taylor approximation of cjy around z.
Plus a quadratic correction term.
Yeah.
2 times the squared norm of yz, where LCJ is the Lipschitz constant of the gradient of cj.
Okay, this specific structure, cjz plus nabla cjz, yz plus L2yz, this looks familiar. Doesn't this guarantee that bar jyz is convex in y for a fixed z?
Yes, exactly. That's the whole point of this construction. While the original constraint CJY0 might be non-convex, this surrogate constraint, bark JEAZOZ, defines a feasible region that is convex in the variable y for a fixed z. This is a standard trick in sequential convex programming.
Ah, so lifting the problem by adding z allows them to replace the difficult non-convex constraint COZY0 with this convexity surrogate constraint.
Precisely. It makes the inner maximization structurally easier to handle, at least with respect to y.
Okay, and then they define the corresponding lifted functions in 12 and 13. Fspx, the max over yz, yx, the set of maximizers yz, and x plus px.
Right. Now, crucially, they need to show that solving this lifted problem is equivalent to solving the original one.
Do they prove that?
Yes, that comes in lemma 3 and remark 4.
Yeah.
They show that fx, and thus x equals x. The key insight is that if y is a maximizer for the original problem, then the pair, y is a maximizer for the lifted problem.
Okay, so optimizing x is the same as optimizing x. We can work in the lifted space to prove properties, and they'll carry back to the original problem.
Exactly. And this allows them to state their main structural assumption, assumption 1, in terms of this lifted problem. Let's break down assumption 1.
Okay, part 1 is about smoothness of f. LF Lipschitz in x for fixed y, and Elbrecht smooth overall gradient is Lipschitz. Standard stuff.
Yep. Part 2 covers P and Q. Proper, closed, convex, proxt operators are computable. And critically, y Adam Q is compact, and Q has bounded variation MQ. Boundedness is key.
Part 3 is on the constraint C. Each Cj is Lj smooth, gradient is Lipschitz, and also twice continuously differentiable. Need that for the analysis involving Barkwold.
Right, and now the big one, part 4, the local KL condition, stated in 15 and 16. This applies to the lifted inner objective F with respect to the inner variables.
Okay, let's read 15. It says there exist constants C0, theta in 12, 1, gamma rho, and sigma C0 such that for a given x, for all yz in a specific set, Lx, an inequality holds.
Right. The inequality is C times the quantity.
Yeah.
Fyz raised to the power theta.
Okay, C, functional gap theta.
Is less than or equal to the distance from 0 to the subdifferential of f with respect to yz evaluated at x, yz. That's just 0 partial yz, fx, yz.
So C, gap theta equals subgradient. This looks like the standard KL inequality form. Theta is the KL exponent. Theta is the strong case, like PL. Theta close to 1 is the weak case.
Exactly. But the crucial part is the set Lx, where this inequality must hold. Look at definition 16.
Okay, Lx contains pairs, yz, in the domain, such that two conditions hold. First, the functional gap fx, x, y, z must be strictly positive.
Right, KL only provides guarantees when you're not already optimal.
And second, this positive gap must also be less than or equal to gamma times dist 0 raised to the power sigma.
This is the localization. The set Lx where the KL property needs to hold depends on how close the outer variable x is to being stationary for the overall problem. S, dist 0 partial x, measures the stationarity of x.
So if x is far from stationary, dist 0 partial x is large. If sigma 0, then the upper bound on the gap, gamma dist sigma, is large, meaning Lx is a potentially large set. The KL condition has to hold over a wider range of YZ points.
Correct, but as x approaches a stationary point of x, dist 0 partial x goes to 0. If sigma 0, the upper bound, shrinks, and the set Lx shrinks, potentially towards the optimal set Yx, the KL condition only needs to hold in an increasingly small region near the optimal inner solutions.
That makes it a much weaker, much more practical assumption than requiring global KL. As Remark 1 points out, many problems, especially Minimax ones, fail global KL right at the solution, but might satisfy this local version.
Exactly. If sigma 0, then dist 0 partial x sigma is just 1, assuming non-zero distance, and Lx requires the gap to be between 0 and gamma. This is more like a standard KL assumption on a fixed level set. But allowing sigma 0 gives this dynamic shrinkage, which is key for broader applicability.
They provide example 1 to illustrate this. A simple minx maxi non is seen plus by 2 with constraints, y and non-pi pi and y2 supposed by 2, 2. They show this fails the global KL condition for the inner problem at yz equals pi 2 when x is large enough.
Right, because at yz pi 2, the subdifferential dist 0 partial y is 0, but the functional gap f x, y, z can be positive by 2 equals 14. This violates the KL inequality 15 if the gap is positive and the subgradient is 0.
But they argue the local KL condition does hold on the set Lx, defined with specific parameters, gamma 18, sigma 0, CSROT 38, theta 12, because when x is far from stationary, Lx might exclude the problematic point, pi 2, pi 2, and when x is close to stationary, the analysis holds.
Yeah, the example really highlights why this localization, controlled by sigma, and the outer stationarity measure dist 0 partial x, is necessary to make the KL assumption applicable to these complex, constrained Minimax problems.
Okay, so we have the setup and the crucial local KL assumption on the lifted problem. Section 2 develops the theoretical consequences. First up is the equivalence result.
Right, Lemma 3 and Remark 4 formally establish that the original maximal function, fx, equals the lifted maximal function, fx, and therefore the original objective psi x equals the lifted objective psi x.
And the proof sketch relies on showing a correspondence between the maximizers.
Essentially, yes.
Yeah.
They show that if y is in y maximizes the original inner problem, then the pair, y is at x, maximizes the lifted inner problem, and there's a connection the other way, too. This ensures minimizing psi is the same as minimizing psi.
Good. So all the structure we assume or derive for the lifted problem directly applies to the original problem we care about.
Exactly. And the first major payoff from that local KL assumption, assumption 1.4, is theorem 1, local Holder smoothness of f.
This is the result you highlighted earlier. It connects the inner problem structure to the outer problem's smoothness.
Precisely. The theorem states two main things. First, the maximal function fx is differentiable on a specific set, u epsilon, which is the set of points x in the domain omega, where x is not epsilon stationary for the overall problem psi. That is where dist 0 partial epsilon.
Okay, so f is differentiable away from stationarity. What is its gradient?
The gradient formula is quite elegant. Nobla fx is simply Nablack's fxy, where y is any maximizer from the optimal set yx.
Ah, that's nice. The gradient of the max function is just the partial gradient of the original f with respect to x, evaluated at the x and the corresponding optimal y. This is related to Danskin's theorem, right?
Very much so, yes. It's a generalization of Danskin's theorem to this constrained, non-convex, non-concave setting enabled by the underlying assumptions.
Okay, differentiability and the gradient formula are great, but the key is the smoothness property described in the bound, 18. This is where the Holder continuity comes in.
Right. Equation 18 bounds the difference nobla fx. Nobla fx. Let's look at the structure. It has two main terms added together. The first term depends linearly on xx involving L-noblo. That's standard Lipschitz-like behavior.
Okay, but it's the second term that captures the non-standard behavior.
Exactly. The second term involves the constants from the KL assumption, c theta, and the smoothness, L-noblo. Looks like 1 theta, c, 1 to theta. Quite a combination.
Multiplied by x raised to the power 1 theta.
Yes. That exponent, nu, 1 theta theta, is the Holder exponent. This term dictates the overall smoothness behavior when theta is not equal to 12.
Let's re-examine the implication of this exponent nu. If the inner problem satisfies the KL condition with theta equals 12, best case, like PL condition.
And nu, 112, equals 1. The second term's dependence on xx becomes linear. So F is locally Lipschitz smooth in this case. The overall bound is just Lxx for some effective Lipschitz constant L.
Which is great. Standard assumptions for many first-order methods hold if theta is 12. But what if the inner problem has weaker structure? Say theta is close to 1. Let's take theta is 0.9.
If beta equals 0.9, then nu equals 1.9, gained 0.1.9 equals 19. The exponent is very small, close to 0.
So the gradient difference nebula fx is bounded by something proportional to xx19.
Right. Since xx19 changes very rapidly near 0, its derivative is infinite at 0. This means F is much less smooth than Lipschitz. It's only Holder smooth with a small exponent.
And this directly impacts the convergence rate we can expect for the outer minimization algorithm, slower convergence, if beta is close to 1.
Absolutely. The convergence analysis of the outer IPG method will explicitly depend on this Holder exponent nu, which in turn depends on the inner KL exponent theta. This theorem quantifies exactly how the structure, or lack thereof, of the inner problem propagates to the smoothness of the outer problem. Hashtag 2.2 local growth property in MFCQ.
Following the smoothness result, Theorem 2 establishes another consequence of the local KL assumption, a local growth property. What does this tell us?
Theorem 2 provides a lower bound on the functional gap for the inner problem, fx, fxy. It says this gap is greater than or equal to some factor times the distance from y to the set of optimal solutions yx raised to a power.
Let's look at the formula 19. The gap fx, fxy is bounded below by some constant factor times dist y, yx raised to the power 1 theta.
Yes, that exponent 1 theta is important. Remember, theta is in 12, 1. If theta 12, the exponent is 112 equals 2. This corresponds to quadratic growth away from the optimal set, which is typical under strong convexity or PL conditions.
And if theta is close to 1, say theta equals 0.9, the exponent is 1.9 equals 1.1 equals 10.
Right. A very high power, meaning the function fx might grow very slowly as y moves away from the optimal set yx.
What's the significance of this growth property?
It's crucial for ensuring that the inner maximization algorithm, the SEP method, makes progress. It guarantees that if y is not optimal, i.e. dist y, yx is large, then the functional gap fsx, fxy is also significantly large, bounded below by this growth condition. This ensures that optimization steps in the y-space yield meaningful improvement in the objective.
And again, this property only needs to hold on that local level set Lx defined in 20, which depends on the outer variable x via disso 0 partial sigma.
Exactly. The required growth property is also localized, just like the KL condition it stems from.
Okay, so we have smoothness and growth properties derived from KL, but we also need to ensure the constraints themselves are well behaved. This brings us to assumption 2. The Mangasarian-Fromovitz constraint qualification, MFCQ.
MFCQ is a standard condition in constrained optimization. It's a requirement on the gradients of the active constraints at any feasible point.
What does it say formally?
Formally, for every feasible point y in the set S, where CVY, there must exist a direction vector tilde, which should technically be tilde y, a direction starting from y, such that the inner product of this direction with the gradient of every active constraint, CJY, is strictly negative.
Active constraints, meaning those j for which CJY equals 0?
Yes, exactly.
Yes.
Let I be the set of indices of active constraints at y. MFCQ required exists tilde in the tangent cone such that nabla CJY tilde y0 for all j and iy.
What's the geometric intuition here? Why do we need this?
Geometrically, it prevents the feasible region S from having degenerate boundary points, like an outward pointing cusp. If you're at a boundary point y, MFCQ guarantees there's always a direction you can move in that simultaneously takes you strictly deeper into the feasible region with respect to all the constraints defining that boundary point.
Okay, and why is that important algorithmically?
It's crucial for ensuring that the Lagrange multipliers associated with the constraints are well-defined and, importantly, bounded. If MFCQ fails, the multipliers might blow up, and the KKT conditions might not hold or be informative. It ensures a certain regularity of the constraint set.
Makes sense. It's a guarantee that the boundary isn't too pathological.
And this MFCQ assumption leads directly to Theorem 3, which is a key property needed for the analysis of the SEP method that uses the surrogate constraint bark.
What does Theorem 3 state?
It says that if MFCQ holds, assumption 2, then for every point z in the feasible set S, we can find another point y, also in the domain y, such that the surrogate constraint function bark, YIZ, is strictly feasible. That is, bark JYZ is strictly less than 0 for all j, and bounded away from 0 by some uniform constant to zeta, where zeta 0.
So for any z we might be evaluating the surrogate constraint around, there's always a point y that satisfies the surrogate constraint with some margin zeta.
Exactly. The proof uses MSEQ essentially to show that such a strictly feasible point y must exist relative to z.
And why is this theorem needed for the SCP algorithm?
When the SCP algorithm solves its subproblem at iteration k, it minimizes an objective subject to bark. Theorem 3 guarantees that this feasible set is non-empty and has a non-empty relative interior. It contains a point y where bark YCK is strictly negative. This is technically important for ensuring the subproblem is well posed, and crucially for deriving the bound on the Lagrange multipliers in lemma 1 later on. It prevents the subproblem's feasible region from collapsing in a degenerate way. All right, let's move on to the algorithms themselves. First up is algorithm 1, the sequential convex programming SCP method. This is the engine designed to solve the inner maximization problem.
Right. For a fixed outer variable x, the inner problem is maxi fxy coy0. This is equivalent to minimizing hy's nash xy plus qy subject to cy0. Let's call the smooth part gy, nash f's xy. So we're minimizing hy's gy plus qy subject to cy0 as stated in 24. It's exactly. Gy is smooth, but potentially non-convex, since f was non-concave. Qy is convex, but potentially non-smooth, and cy defines potentially non-convex constraints. This is the general form of the problem SCP is designed to handle.
Okay, and to guarantee SCP works, to make assumption 3. What does it assume about this inner problem, HY?
Assumption 3 requires two things. First, the smooth part, gy, is assumed to be L-smooth on the domain y. That's standard.
Okay, Lipschitz gradient for G.
The second, and more crucial part, is that an augmented version of the objective, A's WA, satisfies a standard KL condition, 25. This HA is constructed similarly to F, incorporating the surrogate constraint idea, but without the X dependence.
Wait, so the SCP method itself relies on a KL assumption for the problem it's trying to solve?
Yes, but notice the difference. Assumption 1 was a local KL condition on the lifted inner problem F, localized by the outer variable X. Assumption 3 is a more standard KL condition, potentially global, on a level set defined by eta, assumed to hold directly for the structure of the inner minimization problem ACE itself, represented by S. I see. So the overall framework has nested structural assumptions. The outer problem's convergence relies on the local KL of assumption 1, which gives holder smoothness. The inner solver, SCP, relies on its own KL property, assumption 3, to guarantee it can find an approximate solution to the inner problem sufficiently fast.
That's a good way to put it. The guarantees build on each other.
Okay, let's walk through algorithm 1. What's the core idea of SCP?
The core idea is iteration. At each outer iteration k of SCP, we have a current estimate zk. We want to find a better estimate zk plus 1. We do this by solving a simpler, convex approximation of the original problem around zk. This happens in the inner loop, indexed by I.
Right, line 4, the subproblem, 27. This looks like the heart of it. Let's break down what's being minimized here.
Okay, at inner iteration I, for a fixed outer k, we compute zk plus 1, I by minimizing a function of z. The objective function is nabla zk, ztk plus lk, I2z, ck2 plus qz.
Let's parse that. The first term, nabla zk, zck, is a linear approximation of the change in the smooth part g, centered at zk.
Right. The second term, lk a2 zzq2, is a quadratic proximity term, like a trust region, that keeps z close to zk. LKLI is an adaptive parameter.
And the third term is QZ, the simple convex function. So the objective is basically a proximal gradient type of approximation for HEZ plus QZ, linearized around ZK plus the QZ term, and this objective is convex in Z.
Exactly. And crucially, this minimization is subject to the constraint Barch Z0,
Ah, the surrogate constraint we defined earlier, using ZK as the linearization point. And we know this defines a convex feasible set for Z.
Correct. So the subproblem in line 4 is a convex optimization problem. We minimize a convex objective over a convex feasible set. This is generally much easier to solve than the original non-convex problem.
They mentioned the constraint set can be seen as an intersection of Euclidean balls. How does that work?
If you look at the definition of Barch JZ, you can rearrange the inequality Barch JZ 0 into the form ZT2 JZ for some centers K, J, and radius squared RJG derived from LCJ, Nabla CJ, CJ, etc. So the feasible region is indeed an intersection of balls, which is computationally manageable.
Okay, so we solved this convex subproblem to get a candidate point zk plus 1I, but is it guaranteed to be a better point for the original non-convex problem, HDZ?
Not necessarily, because it was based on an approximation. That's why we need line 5, the line search.
Right, this looks like a standard sufficient decrease condition. We check if the original objective H evaluated at the candidate point, HCK plus 1I, has decreased enough compared to HDK.
Specifically, the condition is HCK plus 1I, HCK, beta 2, ZK plus 1I, CK, where beta is some constant, like LKY is 2. We need the decrease to be proportional to the squared step length.
And if this condition fails?
If it fails, it means our approximation was too aggressive, likely because the parameter LKI was too small. So we increase LK, line 7, resolve the convex subproblem, line 4, with a larger LK, it pulls the solution closer to Z, and check the decrease condition again.
We repeat this inner loop, increasing LK, until the sufficient decrease condition is met.
Yes. Once it's met, we accept the point Z plus 1 as our next outer iterate Z plus 1, and we record the corresponding Lagrange multipliers lambdac from the subproblem's KKT conditions.
Okay, that makes sense. Iterate by solving convex approximations, ensure sufficient decrease in the true objective. Now, how does SCP know when to stop? Line 10. The termination criterion. It looks complicated.
It does look intimidating. Let's try to understand the intuition. It's comparing the squared norm of something related to the subproblem's stationarity condition to a tolerance tau.
The term inside the norm involves nabla gk plus 1, nabla gck, the actual change in gradient, compared to terms involving lk and the step plus 1's gay, plus constraint-related terms involving the multipliers lambdac and constraint constants.
Yeah. The key insight comes from lemma 8 later in the paper. This termination criterion, 28, is cleverly designed so that satisfying it implies that the distance from 0 to the subdifferential of the augmented objective, dist 0 partial plus 1 zk, is less than or equal to sucre tau.
So stopping condition 28 is actually a proxy for ensuring that the solution z plus 1 is approximately stationary for the augmented problem OPSA, which incorporates the surrogate constraint logic.
Exactly. It connects the computationally verifiable condition 28, based on the SCP steps, to the theoretical stationarity measure needed for the overall convergence analysis.
The tolerance tau will be set by the outer loop based on the desired final accuracy epsilon. Hashtag 3.3 theoretical guarantees for SCP.
Okay, so we have the algorithm. Does it work? Theorem 4 seems to address well-definedness and properties. Yes. Theorem 4 first guarantees that the inner line search loop, lines 5 to 8, always terminates. You won't get stuck increasing LKO ever. In fact, it terminates in a bounded number of iterations, bar A plus 1, where bar A depends only logarithmically on the smoothness constants L and beta. So the inner loop is efficient.
Good. What else?
It also shows the step size parameter LK used in the successful step remains bounded between L and some upper bound bar L. It doesn't explode or vanish.
And part 3 mentions KKT conditions.
Right. It states the first-order optimality conditions, KKT conditions, satisfied by the solution ZK plus 1 and the corresponding Lagrange multipliers lambdac obtained from the final accepted subproblem, 27. Equation 30 is the complementarity condition. Lambdac bar JK plus 1 is EK 0, though here it uses the relation derived from KKT, and 31 is the stationarity condition for the Lagrangian.
That stationarity condition 31 looks like 0 belongs to nabla G plus LK plus 1 ZK plus partial Q plus 1 plus some lambdac nablas plus 1 ZKK. This is the subdifferential stationarity for the subproblem's Lagrangian.
Precisely. These conditions are essential for the subsequent analysis.
Now, a key piece seems to be lemma 1. Bounding the Lagrange multipliers, it says lambdac 1, the L1 norm of the multipliers, is uniformly bounded by some constant A. Why is this so important?
In many optimization algorithms involving multipliers, convergence proofs break down if the multipliers can grow unboundedly. Bounding them is crucial for stability and for deriving complexity results that don't depend on the specific iteration K.
And how do they prove this bound? What does it rely on?
The proof relies heavily on Theorem 3, the result derived from MFCQ. Remember, Theorem 3 guaranteed the existence of a strictly feasible point Hattie, such that the Parkatanisque de zeta.
Right, the existence of a Slater point for the surrogate constraint.
They use this Slater point Hattiac in the KKT conditions, specifically the Lagrangian definition bar L, Z is lambda, and combine it with the bounds on the objective function change, using the diameter dy, variation MQ, smoothness bar L, and gradient bound G for G. By comparing the Lagrangian value at Z plus 1 and Hattiac, they can derive the upper bound A on lambdac 1 that depends on zeta, dy, MQ, etc., but not on K.
Okay, so MFCQ, via theorem 3 and zeta, is absolutely essential for getting bounded multipliers, which underpins the rest of the analysis.
Critically important, yes. And with the bounded multipliers and other properties established, they can finally prove the convergence rate in Theorem 5.
This theorem connects the decrease in the objective function h to the KL property assumed in assumption 3. It uses lemma 9, which relates the stationarity measure dist0 partial h back to the objective decrease using KL.
Right. The core technical step, equation 65 in the appendix, derived in lemma 9, shows that the reduction in a potential function, OL plus 1 to k, where alpha depends on the KL constant c and other problem parameters. This is a classic consequence of the KL inequality.
A recurrence relation based on the KL exponent zeta, and this implies convergence.
Yes. This recurrence guarantees that the algorithm terminates, i.e. satisfies the stopping condition 28 with tolerance tau, in a finite number of iterations, k theta.
And the complexity k theta depends strongly on theta.
Absolutely. Let's look at the results.
If the theta is 12, the PL-like condition, strong structure.
And the complexity wet is O log. You can tell. Logarithmic convergence. That means the number of iterations grows very slowly as you demand higher accuracy, smaller tau. It's extremely fast.
But if theta is in 12, 1 weaker KL structure,
then the complexity k theta scales like O tau. Now theta. Wait, let me reread the theorem statement's dependency. The theorem bounds the number of iterations k needed to reach h is e k h tau. The complexity depends on how little this 1 relates to ball plus 1. Using the assault OLL plus 1 alpha disteral partial O to ZL plus 1 solitaire. The KL property to CL plus 1, we get RLL plus 1 alpha C2 RL plus 1 theta. This is the key recurrence.
Okay, RL L plus 1 plus 1 plus 1 2 theta. How does this lead to the iteration count?
This is a standard argument for KL convergence. If 2 theta 1 i.e. theta 12, you get linear convergence, RL plus 1, which means O log tau iterations to get RK and tau.
Makes sense for theta 12.
If 2 theta 1, i.e. theta in 12, 1, the convergence is sublinear. Summing the inverse relation roughly gives that the number of iterations k needed to reach RK tau scales, like OR RL0 2 theta 1, tau at theta 1, which simplifies to OT if tau is small.
So the number of SCP iterations k theta needed to achieve an inner accuracy tau scales like O log tau if theta 12 and O to theta in 12, 1.
Exactly. The closer theta is to 1, the larger the exponent to theta 1 is approaching 1, and the slower the convergence, steeper polynomial dependence on tau. But the crucial point is, it's always a finite number of iterations. Assumption 3, KL, guarantees finite time convergence for the inner SCP loop, with a rate determined by theta.
Okay, so we have SCP, algorithm 1, as a provably convergent solver for the inner maximization problem, assuming KL structure, assumption 3. Now we need to embed this into an algorithm for the outer minimization problem, minx pacex, where tieso fx plus px.
Right, and the challenge is that cpace is non-smooth, because fx, the maximal function, might only be Holder smooth from theorem 1 and px is convex but possibly non-smooth. Furthermore, we can't even compute fx or its gradient nabla fx exactly, because that would require solving the inner maximization perfectly.
So we need an algorithm that can handle non-smoothness and only requires approximate information about fx.
Precisely. That's where algorithm 2, the inexact proximal gradient method, IPG, comes in. The core idea is to run a proximal gradient method on, say, x, but using an inexact gradient for the SX part.
What do we use as the inexact gradient?
At iteration k, where we have the outer iterate xk, we also maintain an approximate inner solution yk. We then use nablags, fxk, yk, the partial derivative of the original smooth function f evaluated at the current iterates, as the approximation for the true gradient nabla fxk.
Okay, that seems plausible, but we need to control the error introduced by using this approximation.
Exactly. The analysis needs to show that if yk is computed sufficiently accurately by the inner SCP solver, then the error between nablags fxk, yk and the true nabla fxk is small enough for the outer algorithm to converge.
Before diving into the algorithm steps, they define some parameters in 37 and 38. Based on the target accuracy epsilon and the KL parameters, gamma, sigma, theta, there's a radius r, constant m, and the Holder exponent, new one set again.
Yes, these are needed for the analysis and the algorithm definition. The radius r defines a local region around the current iterate where the proximal step is taken. It depends on gamma epsilon sigma, connecting it to the local KL conditions parameters. Dou is just a Holder exponent we saw in Theorem 1.
And they state a core observation around equation 39. What's the idea here?
The observation leverages the local Holder smoothness of F, Theorem 1. It basically says that in a small ball, BXO, around a non-stationary point X, The potentially complicated function pxx plus px can be bounded above by a simpler function, tx plus approxgrad xx plus lk2x plus px. This is a standard type of upper bound used in proximal gradient analysis, but here LK incorporates the Holder smoothness constant.
So locally, Cx behaves nicely enough that a proximal gradient step based on an approximate gradient is guaranteed to make progress, provided the step size, when Lk, is chosen appropriately based on the Holder properties.
That's the intuition, yes. It justifies the structure of the IPG step.
Okay, let's trace the steps of algorithm 2 itself. How does it start?
Initialization requires a starting point Mas0 and also an initial inner point Mas0. Crucially, Y0 needs to be a reasonably good approximation of the true maximizer for X0. The condition is Fx0, F0, Y should be less than minima epsilon sigma 2, Y.
So we need to pre-compute a decent Y0 perhaps by running SCP at 0 for a bit?
Yes, that's implied. You need a good starting Y0 that satisfies this initial accuracy relative to the target epsilon and the KL parameters gamma, sigma.
Okay, then we enter the main loop, KO012. Line 3 defines sequences deltac and etac for controlling inexactness. They both go to 0 like 1k plus 1.
Right. Deltac will likely control the error allowed in the gradient approximation, and etac will control the accuracy required from the inner SCP solver. They decrease as the algorithm progresses, demanding more accuracy over time.
Line 4 is the outer proximal step. This looks like the core update for X.
It is. Xk plus 1 is computed by minimizing a function, nablax fxk, x plus bar lk2x, sk2 plus px. This minimization is also constrained. X must be in the ball, be xk here.
Let's break down that objective. The first term uses the inexact gradient nablax, fxk, yk. The second is the quadratic proximal term with step size 1 bar. The third is the simple convex function, px.
So this is exactly the proximal gradient update step, but using the approximate gradient nablax fxk, yk instead of the true nabla sk. The constraint x in bhkr keeps the step localized, which might be needed because the gradient approximation is only guaranteed to be good locally.
Okay, so we compute xk plus 1 using this inexact proximal step. Now we need to update y to match this new xk plus 1. That's line 5.
Line 5, the subroutine call, yes. We need to find the corresponding approximate inner maximizer yk plus 1 for the new outer iterate xk plus 1.
How do we find yk plus 1?
We call our trusty inner solver algorithm 1, SCP. We ask it to approximately solve the inner maximization problem defined at xk plus 1, that is, SCP minimizes hy net xk plus 1, y plus qy subject to cy.
And we initialize SCP using the previous inner solution, yk.
Yes, using yk as a warm start for SCP is crucial for efficiency.
Now, how accurately does SCP need to solve this inner problem? Does it need to run until full convergence?
No, that would be too expensive. This is where the inexactness comes in. The termination tolerance tau for algorithm 1 is set dynamically. It's set based on the overall target accuracy epsilon and the current outer iteration's accuracy parameter etac plus 1, which is related to 1k plus 1.
Ah, so the required accuracy for the inner solution yk plus 1 increases as the outer loop progresses, as etac plus 1 decreases.
Exactly. In the beginning, we only need a rough yk. As xk hopefully gets closer to the solution, we demand a more accurate yk plus 1 from SCP to ensure the gradient approximation at Black's fxk plus 1 remains good enough.
This seems like a very elegant interplay. The outer loop takes an inexact proximal step. The inner loop, SCP, is called to provide just enough accuracy for the next outer step, and the required inner accuracy tightens over time.
That's the essence of the inexact proximal gradient method, coupled with the SCP subroutine. It balances the computational effort between the inner and outer loops dynamically. Hashtag tag 4.3 complexity analysis.
Okay, we understand the algorithm. Now for the crucial part. Proving it converges and finding the complexity. This involves several lemmas. Lemma 2 seems important.
Lemma 2 establishes that the Lagrange multipliers generated by the inner SCP calls, algorithm 1 running inside algorithm 2, remain uniformly bounded by some constant f.
Didn't we already bound the multipliers in Lemma 1?
Lemma 1 bounded them for a standalone run of SCP on a fixed inner problem H. Lemma 2 extends this to the context of algorithm 2, where the function gy-fxk plus 1y changes at each outer step k plus 1. It confirms that the multipliers remain bounded even as x changes, relying on bounds on the gradient of f, gf. This ensures the inner SCP runs remain stable throughout the outer iterations.
Got it. Then Lemma 10 provides the key bounds. It says that if the outer iterate XL is not yet stationary, then the approximate inner solution L are obtained by calling SCP with the dynamically chosen tolerance tau, related to EDL, satisfies two crucial properties, equations 72 and 73.
What are those properties? First, the functional gap fxl, yl is small, controlled by Edel. Second, and most importantly, the norm of the difference between the true gradient nabla FSLIL and the approximate gradient nablax FSLIL is also small, again controlled by Edel and the problem constants, including KL parameters.
So lemma 10 formally proves that running SCP to the specified tolerance Edel guarantees that the gradient approximation error is small enough. This validates using nablax FSLIL in the outer proximal step.
Exactly. It's the theoretical justification for the inexact part of IPG.
With these lemmas in place, we can get to the main results. Theorem 6 and 7, the complexity bounds.
Theorem 6 gives the iteration complexity. It states that algorithm 2 finds an epsilon or stationary point xk in, at most, kapsilon iterations.
And kapsilon, looking at the formula, it's a beast. It involves epsilon raised to various negative powers combined with the KL parameters theta, sigma, gamma, c, and other problem constants, LF, m, etc., plus logarithmic factors.
It is complex, but the key is the scaling with respect to epsilon. If you analyze the dominant terms, the complexity kapsilon scales roughly like epsilon max plus nu sigma times polylog factors. Remember, nu, 1 theta theta.
Let's try to simplify that exponent. 1 plus 1 theta theta, 1 plus theta theta, plus 1 theta theta, 1 theta, 1 clue theta.
Good simplification. So the exponent is max 1 theta, 1 plus nu sigma. Let's recheck the paper. The derivation in the appendix leading to Theorem 6 suggests that complexity might be closer to O epsilon max 2, 1 plus nu sigma. Let's stick to the paper's claim interpretation, epsilon epsilon. This highlights the dependence.
Okay, so the number of outer iterations depends polynomially on 1 epsilon, and the exponent of that polynomial is determined by the KL exponent theta via 1 out theta and the shrinkage parameter sigma via sigma theta.
It's exactly. Better KL structure, smaller theta closer to 12, leads to a smaller exponent, 1 theta, meaning faster convergence. Similarly, the impact of sigma is modulated by theta.
Okay, that's the number of outer iterations. But each iteration involves calling SCP, which itself takes multiple steps. What about the total work?
That's Theorem 7, first-order oracle complexity. This measures the total number of gradient evaluations, nabla F or nabla C, needed, which is often a better measure of overall computational cost.
It says the total oracle complexity n epsilon is the sum of the outer iterations kapsilon plus the total number of inner SCP iterations n epsilon, and it gives a bound on epsilon.
Right. The total complexity involves multiplying the number of outer steps by the complexity of each inner SCP call. Remark 3 summarizes the resulting asymptotic complexity, which is even more complex than for kapsilon.
Let's look at the simplified cases in Remark 3.
Case 1. If theta here is 12, best case KL for inner problem, the total oracle complexity becomes over epsilon max 1 sigma log 1 epsilon 2.
So if sigma is also small, say sigma 1, we get roughly O epsilon 2 polylog. That's a pretty standard and efficient rate for non-convex optimization, similar to what you'd expect for finding stationary points of smooth functions.
Exactly. If the inner problem has the best KL structure, the theta 12, the overall algorithm is quite efficient.
Case 2. If theta is in 12, 1, weaker KL structure. Now the complexity exponent becomes much worse. It's O epsilon exponent polylog, where the exponent involves a complicated fraction 2 theta plus 1 theta, multiplied by that max 1 theta, sigma theta term.
Yeah, the exponent gets significantly larger than 2, especially as theta approaches 1.
So the takeaway is crystal clear. The overall complexity of finding an approximate stationary point for this constrained non-convex-nonconcave minimax problem depends critically and polynomially on the quality of the KL structure, theta, of the inner problem and the localization parameter, sigma.
Absolutely. Weaker structure means significantly more computational effort is required to reach the same accuracy epsilon. But importantly, the theorem still provides a finite complexity bound, which is a major theoretical achievement for such a difficult problem class.
Okay, after all that heavy theory and complexity analysis, they provide some numerical results in Section 5 to show that this actually works in practice.
Right. Theory is great, but seeing it run is important. They tested on a specific constrained minimax problem defined in 43.
Let's look at the setup. It's minx-maxi of an objective involving Hadamard products, element y's multiplication, of y plus x and y plus bx, where a and b are matrices, plus L1 regularization terms by 1 and y1, and box constraints on X and Y.
So Px is the L1 norm plus indicator for a box. Qy is the L1 norm plus indicator for a box, -2, 2, and 2. The core function fxy involves those Hadamard products. This looks like a non-trivial coupled non-convex-nonconcave objective.
And crucially, they add explicit functional constraints. Cjy equals 0, defined in 44. They use exponential functions. Cjy xty plus xpyjcj equals 0.
These constraints are convex, actually, Cauchy-like. They note that on the domain y having 2, 2, and 2, these constraint functions Cj are LGJ smooth with LGJ2. This verifies assumption 1-3 that the constraints are smooth.
Okay, so they've constructed a test problem that fits the structure of problem 1 they analyzed. How did they implement the algorithm?
They generated the matrices A and B randomly, standard normal distribution. They set the key KL parameters for the analysis based on assumptions. C 0.1, theta 0.5, assuming the best case inner structure for simplicity, gamma 0.01, sigma 0.1. They set the target accuracy epsilon 10 to 2.
And they initialized at x0, y0, 0, 0, 0, noting that y0, 0 is feasible and satisfies the initial accuracy requirement for the inner problem easily since f0, 0, 0.
Right. Then they ran their algorithm too, IPG nesting SCP.
How did they evaluate the performance? What metrics did they use? Table 1.
They used two main metrics to evaluate the quality of the final solution epsilon found by their algorithm. The first metric is the actual final objective value, denoted size epsilon. To calculate this, they need the true f epsilon, which means they have to solve the inner maximization problem maxi f epsilon y exactly or very accurately using an external, potentially slow global solver, like MATLAB's global search.
Okay, so psi epsilon is the ground truth objective value at the point their algorithm stopped. What's the second metric?
The second is the approximate final objective value, denoted happy f epsilon. This is calculated using the approximate inner maximizer epsilon that their algorithm 2 actually computed alongside epsilon. So happy epsilon, f epsilon plus p epsilon.
Ah, I see. So psi uses the true max value f, while happy uses the value f achieved by the algorithm's approximate inner solution epsilon. Comparing these two tells us how good epsilon really was.
Exactly. If happy is very close to psi, it means the inexact solution epsilon found by the inner SCP loop was indeed a very good approximation of the true maximizer.
And what do the results in Table 1 show? They tested different dimensions, N1, N2.
The results look quite convincing. First, the final objective values, both high and happy are significantly lower than the initial objective value 5x showing that the algorithm successfully found a much better solution, a deep minimum in this case. For instance, for N1, N2, 150, the value dropped from around 1.42 to about -580.
That's a huge drop. Okay, so it finds good solutions. What about the comparison between psi and hat-pi?
They are very close across all tested dimensions. For N1, N2, 150, chi-ice epsilon was -579.71, and happy-ice epsilon was -579.73. The difference is tiny.
That's excellent validation. It suggests that the whole theoretical framework of using the inexact inner solution epsilon works extremely well in practice. The fast approximate SCP solver provides an inner solution that's good enough for the outer IPG loop to converge to a point where the corresponding approximate value is almost identical to the true value.
Precisely. It's practical evidence that the hybrid SCP-IPG approach, built upon the local KL theory, successfully balances accuracy and efficiency to solve these complex constraint problems. #outro. So just to recap the high points of this deep dive, this paper really provides a complete, rigorous framework for tackling these notoriously difficult, constrained, non-convex, non-concave Minimax problems.
Yeah, the journey was quite technical.
It was. But the key theoretical steps were establishing that equivalence of the lifted problem, which was the key to unlocking the structure.
Right, making the inner constraint convex in Y.
And then using that lifted structure to prove the crucial property, the local Holder smoothness of the maximal function f, which was derived directly from assuming that local Kurdyka-Łojasiewicz condition on the inner lifted problem.
And that Holder smoothness, in turn, dictated the convergence properties of the outer algorithm.
Exactly. And the algorithm itself, that hybrid SCP-APG design, is specifically tailored to leverage this structure. SCP handles the constrained inner part efficiently, assuming its own KL property holds, while IPG handles the outer part using only inexact information from SCP.
So the practical takeaway for you, the listener, if you're dealing with problems like adversarial training, robust optimization, or maybe certain game theory models where you have these minimax structures with non-convexities and hard functional constraints on the maximizing player.
You now have a method with rigorous finite time convergence guarantees. You're not just relying on heuristics anymore.
And crucially, you know exactly which structural properties those guarantees depend on. Primarily the KL exponent theta of the inner problem and that localization or shrinkage parameter sigma from the local KL assumption.
The ability to actually analyze these incredibly difficult problems and get concrete complexity bounds, even if they are sometimes complex bounds, is just a massive leap forward.
Okay, that brings us to our final provocative thought for you to mull over. We've seen that the entire performance, the computational budget required, is fundamentally dictated by these parameters, theta and sigma, and the constant c, that describe the hidden geometric structure of your problem via the KL condition.
Better structure, theta near 12, means faster algorithms.
So the challenge we want to leave you with is this. Can you move beyond just assuming these parameters exist? Can you develop techniques to actually estimate or bound these constants theta, sigma, c a priori for specific problems you care about?
Imagine, for instance, you're designing a particular Jan architecture with specific activation functions and constraints. Could you mathematically analyze that specific structure to determine, or at least tightly bound, the KL exponent theta that governs its inner maximization? The discriminator's problem.
Or if you're setting up a distributionally robust optimization problem with a certain ambiguity set defined by constraints, can you analyze the geometry of that set and the loss function to get a handle on theta and sigma?
If you could do that, if you could estimate these structural parameters before running the optimization,
you could then use the complexity theorems, like Theorem 7, to predict the computational cost required to reach a desired accuracy epsilon. You'd move from purely empirical trial and error to predictive optimization design.
Knowing the complexity cost before you launch that massive training job, that would be the ultimate payoff from deeply understanding this kind of theoretical work.
Something to think about. We hope this deep dive was insightful. We'll catch you next time for more technical synthesis. Okay, let's unpack this. We are diving deep today, really deep, into a domain that's, well, it's kind of the engine room for a lot of modern AI. You know, think generative adversarial networks, robust training techniques.
Absolutely, it's fundamental.
Yeah.
But it's also one of the areas with some really deep theoretical challenges remaining.
Exactly. And our deep dive today is focused squarely on one of those challenges. Constrained, non-convex, non-concave minimax optimization. That phrase itself tells you we're heading into rugged territory.
It really is the next frontier, you could say. We've seen, tremendous progress in Minimax optimization over maybe the last decade, but a lot of that success relied on some simplifying assumptions.
Like what specifically?
Primarily around the inner problem, often assuming it was unconstrained or maybe had very simple constraints like box constraints. The complexity just explodes, exponentially, when that inner maximization variable, the IID player, is bound by complex, potentially non-convex constraints.
And that's our mission today, isn't it? We're going beyond just a surface summary of this new paper. We want to zero in on the technical core. The real question is, how exactly do we guarantee convergence? And by convergence, we mean finding approximate stationary points, which is often the best we can hope for here.
Right, because global optimality is usually off the table.
So how do we find these stationary points when the objective function is, well, messy? It's non-convex in the variable we're minimizing, non-concave in the variable we're maximizing, and that maximizing player has to navigate this really complicated, restricted landscape defined by constraints.
It's a tall order, and we'll explore the specific tools the authors bring to bear. First, there's the strategic application of the Kurdyka-Łojasiewicz condition, the KL condition, but critically they apply it locally, not globally. That's a key distinction.
Okay, local KL. What else?
And second, a really quite clever sequential convex programming approach, or SCP. It's designed specifically to grapple with those difficult inner constraints.
So this deep dive is really about the why and the how. How do these pieces fit together? How do they bridge that gap between, really challenging theory and actually getting practical first-order algorithms that work?
That's the goal, to understand the machinery they've built.
Right. So before we get into the machinery, let's really establish the battlefield. We need to look closely at the foundational structure, which the paper calls problem 1. Everything else sort of builds on this.
Absolutely. Foundational is the right word. Okay, so problem 1 is formally defined as, let's vocalize it carefully, the minimization over the variable $6.
Okay, so $6 is trying to minimize something.
Right. Minimize the result of an inner problem. And that inner problem is the maximization over the variable Yas.
Minimax, the classic Minimax setup.
Exactly. But there's a constraint on Yas. The maximization is subject to the condition that a CIEA is less than or equal to 0.
So you can't just go anywhere. It has to stay within the region defined by this function, 6 now.
Precisely. And what are they maximizing? It's the objective function inside. $5 to y plus parentheses dollars minus $2.
Okay, wow. That is dense. Let's try to break down the roles here. I often find it helpful to think of this as maybe a two-player game, a kind of tug of war, where the function value is the score they're fighting over.
That's actually a great analogy. Player $6, the outer one, is the minimizer. They want the lowest score possible. Player Y, the inner one, is the maximizer. They want the highest score possible.
But it's not like they take turns sequentially, right? It's more simultaneous.
Well, conceptually, yes. The structure implies that player sellers has to choose their strategy, their value for 6, knowing that whatever $6 they choose, player will respond optimally. Player Zhao will choose the best possible dier from within their allowed constraint set to maximize the score.
Ah, okay. So $6 has to anticipate Yaller's best response. That's the core of the Minimax idea.
Exactly. $6 has to minimize the outcome after Zhao has done its worst, or rather, its best from its perspective.
Got it. Okay. Let's look at the pieces inside that objective function now, starting with duck y. That seems like the main interaction term.
It is. Find why y is really the source of the primary difficulty, the non-convex, non-concave nature. The paper assumes it's smooth, differentiable, which is, a helpful starting point.
Smoothness is good.
But critically, it's generally non-convex with respect to 6. So if you fix dock and look at the function, just in terms of 6 docks, it might have multiple valleys, bumps. It's not a nice, simple bowl shape.
Okay, so minimizing over $6 are already hard.
And simultaneously, it's generally non-concave with respect to Gus. So if you fix $6 and look at it just as a function of $, it's not a nice single peak either. It might have multiple peaks or flat regions. Non-concave is just the negation of concave, meaning it's not shaped like an upside-down bowl.
So the overall landscape this function fix-y describes is potentially really rugged. Hills, valleys, saddle points. It's complex.
Extremely complex. And this is crucial. It means we don't have the luxury of assuming convexity or concavity to guarantee that any local solution we find is the global one. We're likely going to find stationary points, which could be local minima for $6, local maxima for U, or saddle points.
Right. So standard convex optimization techniques won't just work out of the box. We can't rely on finding the single best answer easily.
Precisely. Now, what about the other terms, Px and Tugals? They seem simpler separated.
Yeah, they're only functions of one variable each.
Right. These are typically introduced to handle things like regularization or simple constraints on the variables themselves. The paper assumes they are simple, closed, convex functions.
Convex. Okay, so these parts are nice.
They are. Simple often means their proximal operator can be computed easily. For instance, if you wanted to constrain $6 to be non-negative, Px could be the indicator function for the non-negative orthant. It's 0 if $6 is non-negative, and infinity otherwise.
Ah, okay. So it enforces a hard constraint. Or it could be like an L1 or L2 regularization term.
Exactly. Things like L1 norm for sparsity or squared L2 norm for Tikhonov regularization. These are convex. And the same logic applies to Plochwise. It might enforce simple constraints on YOM or add regularization. Their convexity is key, because it allows us to use efficient proximal operators, which are fundamental building blocks in many first-order optimization algorithms.
Got it. So 4x is the complex, coupled, non-convex, non-concave part. 4x and y are simpler convex regularizers or constraint handlers.
Correct. And then there's the element that really defines the specific challenge this paper tackles, the constraint.
It's just the constraint on the inner player.
Yes. And this is really the heart of the difficulty added in this work compared to much of the prior art. The function is assumed to be smooth, but it can define a potentially highly complex, possibly non-convex constraint set for YAL.
So the playground for player dollars isn't necessarily a simple box or a sphere. It could be a really weird shape.
It could be a very weird shape, possibly even disconnected regions. Remember our game analogy. Player users trying to maximize the score, but they are strictly confined to operating within this potentially very complex, rugged boundary defined by FAMF.
What if Sanders was simpler? Like if Thatter defined a convex set?
Well, if Neller defined a convex set, if $7 was a convex function or represented linear constraints, then the inner maximization problem, while still potentially non-concave in HODG due to fair dollars, would be maximization over a convex set. That's often much easier to handle, sometimes solvable globally, if the dollar had better properties and times. But here, the paper explicitly allows for general, smooth, potentially non-convex dollars. That's the core challenge.
Okay, this really paints the picture. We're trying to find in $6, the $6 player wants to minimize the final score. But the score is determined after the dollar player makes their move. And the dollar player maximizes the score, but is restricted by this potentially nasty constraint. $6 to $6 has to find the best strategy anticipating dollar's optimal constrained move.
That's it, precisely. It sets the stage perfectly for understanding why standard optimization methods often break down here and why new theory and algorithms are needed. Hashtag 1.2, broader context and penalty methods, problem 2.
Now, you mentioned problem 1 is foundational. Does it appear in other contexts as well?
Yes, very much so. To really appreciate the scope and importance of being able to solve problem 1, we need to see how it connects to an even more general setup, which the paper labels problem 2.
Okay, so problem 1 is a building block for something bigger. What's problem 2?
Problem 2 is, you could say, the fully constrained version. Now, both players face potentially complex constraints. It's formulated as the minimization over 6 subject to a new constraint being less than or equal to 0.
Ah, so 6 is constrained now, too.
Exactly. Subject to x delay s, and the objective being minimized is the same inner maximization problem we had before. The maximization over subject to founder dollar of the function violates plus pxy.
So problem 2 looks like problem 1, but with an added constraint, lex la dollar on the outer minimization variable. Both players might have complicated constraints now.
Correct. Lexler's is assumed smooth, but potentially non-convex, just like CCY. This represents, many real-world scenarios where the decision variable sexil also has operational limits or requirements.
Okay, but the paper focuses its algorithm development and analysis primarily on problem 1, where
Right.
sexil doesn't have that explicit luck constraint, though it might have simple constraints handled by Pipe. Why focus on 1 if 2 is the more general case? How does solving 1 help with 2?
That's a really important practical point. It comes down to a standard but very powerful technique from optimization called the exterior penalty method. The authors point out, and it's a well-established idea, that we can often handle problem 2 by converting it into a sequence of problems that look exactly like problem 1.
A sequence. How does that conversion work? You somehow fold the constraint into the objective.
Precisely. The idea is to penalize violations of the constraint. Instead of enforcing it strictly, you add a penalty term to the objective function that becomes very large if $6 violates the constraint.
Okay, let's get specific. What does that penalty term look like?
You modify the original objective dollar. The new objective for the subproblem becomes 5y plus, a penalty term. This term is typically Le-Caron law applied by the squared Euclidean norm of the positive part of ds. Let's break that down.
Okay, ds sounds like a coefficient.
Yes, ds at is the penalty coefficient or penalty parameter. It's a sequence of positive numbers, row 2, row 3, that must increase towards infinity as scale increases. So now goes to infinity as scale goes to infinity.
So the penalty gets harsher and harsher in later subproblems. Makes sense. What about the rest? The positive part of ds.
Right, that's written as dx plus day using the bracket plus notation, or sometimes max dollars, ds day. It's a simple but crucial operation. For any number or vector roto, plus means you take the component-wise maximum of day as 0.
Okay, so if all x already less than or equal to 0, meaning the constraint is satisfied.
Then the positive part, dollar plus, is just 0. The penalty term is dollar times 0 squared, which is 0. No penalty is applied.
It's like the constraint is invisible when satisfied.
Exactly. But if Dixello violates the constraint, meaning deal becomes positive, or some components become positive if dollar is vector valued.
Then do x plus is that positive violation.
Correct. And then you square the norm of that positive violation vector and multiply it by this potentially huge increasing penalty parameter, dollars and untold. The result is a large positive number added to the objective function, $sim.
Ah, I see. It's like adding a huge cost or barrier that pushes the minimizer $6 away from the infeasible region.
Precisely. As the algorithm is larger and larger across the sequence of subproblems, the cost of violating the constraint becomes infinitely prohibitive. So the solution, $6 less subproblem, which involves minimizing $qual plus psqy over $6 and maximizing over dollars, is forced progressively closer to satisfying dealer.
And crucially, each of these subproblems, you're minimizing over $6 with the penalty added to 5 and maximizing over 6phi that structure.
It looks exactly like problem 1. The penalty term just modifies the phi lie part, but the overall structure fits the template of problem 1.
Okay, that's really significant. It means that if we can develop a robust, theoretically sound algorithm for solving problem 1, that algorithm becomes the core engine needed to solve the much more general, fully constrained problem 2 through this penalty method sequence.
Exactly. It justifies the paper's intense focus on problem 1. Solving it well unlocks solutions for a much broader class of problems. It really highlights the centrality of tackling that inner constraint cell-ejectively.
Makes perfect sense. It's the bottleneck. All right, so we understand the problem structure, its importance, and its inherent difficulty due to the non-convex-non-concave nature and the constraints. Now, how do we actually make theoretical progress? Since we can't rely on standard convexity guarantees for convergence, we need a different tool. This brings us, as you mentioned, to the Kurdyka-Łojasiewicz, or KL condition.
Yes, the KL property has become really the modern workhorse for analyzing the convergence of optimization algorithms in these challenging non-convex settings. It's a concept from real algebraic geometry originally, but it's found huge application in optimization.
Conceptually, what does it give us? What does it measure?
At a high level, the KL property provides a way to relate the value of the function to the norm of its gradient, or subgradient for non-smooth functions, near a stationary point. It essentially quantifies how sharp or valley-like the function is around its critical points.
How does that help with convergence?
Think about what can go wrong in optimization. An algorithm might get stuck because the function becomes extremely flat near a point that isn't actually a minimizer. The gradient becomes tiny, the steps become tiny, and you stop making progress even though you're not at a solution.
Okay, like crawling across a vast plateau.
Exactly.
Yeah.
The KL condition, if a function satisfies it, mathematically prevents this pathological flatness around stationary points. It guarantees that the function value must decrease sufficiently fast as you move away from the set of stationary points, or conversely, that the gradient norm cannot be too small unless you are truly close to a stationary point, and the function value is also close to the stationary value.
So it provides a connection.
Yep.
If the gradient is small, you must be close to a stationary point in terms of position and function value. It links objective descent to distance to stationarity.
Precisely. It ensures that the subgradient norm provides a reliable measure of how far you are from optimality, at least locally. This link is what allows us to prove convergence rates for algorithms even without convexity.
Now, I know in some earlier work, especially in Minimax optimization, people often use the Kurdyka-Łojasiewicz, or PL condition. How does KL relate to PL?
That's a good point. The PL condition is actually a special case of the KL condition. The general KL property involves a function, line of theta, and an exponent, the theta theta. The PL condition corresponds to the specific case where Brbo, say to os to 2, for some constant CDR, which is equivalent to the KL condition holding with the exponent theta equals 12.
Ah, so KL is more general. Why the need for generalization? Is PL too restrictive?
PL is quite restrictive, yes. While it holds for strongly convex functions, it also holds for some non-convex functions, but it's still a strong assumption. Many important functions in machine learning, especially those arising from deep networks or involving non-smooth regularizers, do not satisfy the PL condition globally. However, they often do satisfy the more general KL condition locally, perhaps with an exponent theta that's larger than 12, maybe closer to 1.
So moving from PL to KL allows the theory to cover a much broader, more realistic class of objective functions encountered in practice.
Exactly. It extends the reach of convergence analysis significantly. The KL exponent, theta, which typically lies in the interval $12, becomes a crucial parameter characterizing the geometry of the function near its stationary points.
Okay, so KL is the tool, but you mentioned earlier the authors use it locally. Why the emphasis on local?
This is a major practical and theoretical hurdle. Requiring the KL condition to hold globally across the entire domain of the function is often far too strong an assumption for complex real-world problems. A function might behave nicely near its solutions, but have weird flat regions or other pathologies far away.
So a global KL condition might just fail, even if the function is well-behaved where we actually care about convergence.
Precisely. The real innovation in much recent work, including this paper, is to leverage the power of the KL condition by only assuming it holds locally, in a neighborhood around the stationary points.
Makes sense. Focus the assumption where it matters. But there was another twist you mentioned. They apply it not to the original problem directly, but to a lifted problem. What's that about?
Right. This is a technical maneuver, but it's crucial for dealing with that difficult inner constraint. analyzing the KL property directly for the inner maximization problem. CY is hard because the constraint set itself is complex and defined implicitly.
Okay.
The lifting introduces an auxiliary variable, let's call it Z. They reformulate the inner problem into an equivalent Minimax problem, labeled 14 in the paper, involving both years and years. This new problem is defined over a simpler, explicitly defined constraint set in the combined Z space.
So by adding this variable and reformulating, they trade the implicit constraint for explicit constraints on ZY?
Essentially, yes. The complexity of the constraint gets encoded into the structure of the new lifted objective function, which they call phi x, y, z, f bar. This transformation allows them to apply the KL analysis more readily, because now they're analyzing a function $5 with respect to VZ over a potentially simpler domain.
It's like changing coordinates to make the problem structure easier to analyze with existing tools.
That's a good way to put it. Now they can impose their key assumption, assumption 1, which states that this lifted function satisfies the KL property locally with respect to the inner variables for any fixed outer variable $6.
Okay, let's dig into that local KL assumption. It's assumption 1. You mentioned it introduces several parameters and involves a level set. Can we break that down?
Yeah.
Formula 16 defines this letter.
Yeah, the assumption states that for point Z, within a specific level set, a certain inequality holds. This inequality involves 4 critical parameters that characterize the local geometry. First, there's a constant dollars. Second, the KL exponent, the theta, which we know is in 12 tower. Third, a positive scalar Debato. Fourth, a non-negative shrinking parameter sigma. Sigma. Okay,
C, theta, gamma, sigma. And the inequality itself. It relates function values to gradients, right?
Yes. It relates the gap in the objective function to the norm of the subgradient. Specifically, it involves a difference which takes x, y, z, where fistus is the optimal value of the lifted inner problem for a fixed sextus. This gap must be positive for the condition to apply.
So it only applies if fistus is not already an optimal solution for the inner problem.
Correct. And the KL inequality then states something like bistus, sextus, dilus y z, partial sixt x, y. Here, dis is the desingularizing function related to the KL exponent istus, and partial cis is the subdifferential of the relevant lifted potential function with respect to du of x. This links the function gap to the subgradient norm.
But the paper formulates the level set using these parameters differently. Let's look at formula 16. The x is the set of such the function gap, if it is positive, but bounded above.
Oh, right. They define the region where the KL property needs to hold.
Right.
GALE contains the points, where the gap, xy, xy, z, is greater than 0, but less than or equal to GABA times the distance from 0 to the subdifferential of SOPERSPECT raised to the power sigma.
Wait, the distance term involves the subdifferential with respect to 6y, the outer variable.
Yes, that's a subtle but critical point in their specific formulation. The size of the level set, the region where the inner KL property is assumed to hold, depends on how close the outer variable sigma is to being stationary for the overall minimax problem.
Okay, that's interesting. Let's unpack the implication of that parameter, sigma. It's non-negative. What happens if sigma is scholars?
If sigma is scholars, then that distance term raised to the power sigma just becomes 1, assuming the distance is non-zero. So the upper bound on the gap is just gamma. The level set is a fixed height, gamma.
And if sigma
is positive, then the size of the allowed gap depends directly on how close sigma is to satisfying the stationarity condition for the outer problem, measured by text 0, partial sigma. If sigma is far from being stationary, this distance is large, and the allowed gap, kechnik sigma, is large. So the text bus is a large set.
So the KL condition is required over a wider range of inner points if the outer variable $6 is far from its own solution.
Correct. But as the outer algorithm progresses and $6 gets closer and closer to a stationary point for sigma, that distance term partial sigma shrinks towards 0.
And if sigma dollars, then the term textisma also shrinks towards 0.
Exactly. This means the maximum allowed objective gap at kextisma for points to be included in 6 also shrinks. The KL condition on the inner problem is only required to hold in a progressively smaller and smaller neighborhood sigma gali dollars as the outer variable 6 ball approaches stationarity.
Wow, okay, that's subtle. It's a local KL condition on the inner problem, but the locality itself, defined by LaTeX, is dynamically adjusted based on the progress of the outer problem controlled by sigma.
Precisely. A very elegant way to formulate the assumption. It basically says, we only need the strong KL convergence property for the inner problem to hold tightly when we are already quite close to solving the overall minimax problem. Far away, the condition can be looser. This makes the assumption much more likely to hold for real problems compared to a uniform or global KL assumption.
That sigma parameter seems really important then, controlling how quickly that neighborhood shrinks.
It is. We'll see it reappear in the complexity analysis later. It captures a key aspect of the problem structure. Hashtag 2.3, the maximal function, and local holder smoothness. Theorem 1.
Okay, that clarifies the sophisticated local KL assumption on the lifted inner problem. Now let's connect this back to the outer problem. Player 6 goal is trying to minimize the overall objective. We know y(x) plus p exos. Let's focus on 5x, the maximal function.
Right. Comma x represents the outcome of the inner maximization game for a given $6. It's formally defined as 5 equals the maximum over Vier, subject to the constraint 6(1)xy. So for any $6, we imagine solving that constrained maximization over Yellers to get the maximum possible value. That value is 5x. This 5x is the effective cost function that the outer player $6 is trying to minimize, plus the simple Potts term.
Exactly. But here's the challenge. Even if xy is smooth, the act of taking a maximum over Euler in a constrained non-concave setting generally destroys smoothness. The resulting maximal function novel x is typically non-smooth, or at best not continuously differentiable in the standard Lipschitz sense.
Why is that a problem?
Most standard gradient-based optimization algorithms rely heavily on the assumption that the gradient of the objective function is Lipschitz continuous. This means the gradient doesn't change too rapidly. It allows you to use fixed step sizes and get strong convergence guarantees. If the parabola isn't Lipschitz continuous, those standard analyses break down. So what can we say about the smoothness of Lackest here? This seems like the payoff for all that work with the local KL condition.
It absolutely is. This leads us directly to Theorem 1, which is a cornerstone result of the paper. It proves that, under their assumptions, including the local KL property on the lifted problem, the maximal function, Vaxtagix, possesses a specific weaker form of smoothness called local holder smoothness.
Holder smoothness. Okay, not Lipschitz smoothness, but something related. What does that mean mathematically? Let's look at the inequality they provide. Formula 18.
Formula 18 provides a bound on the norm of the difference between the gradients of 2 points, 6x, xx. So it bounds vert novel fx.
Okay, how is it bounded?
The bound has 2 parts. The first part looks familiar. It's little times the distance. Here, local of x is related to the Lipschitz constant of the gradient of the original vix with respect to 6x. This is a linear term, just like in standard Lipschitz continuity.
Okay, so part of it behaves nicely. What's the second part?
The second part is the crucial holder term. It's proportional to the distance derivative raised to a fractional power, 1 of theta. Remember, theta is the KL exponent from assumption 1.
Ah, theta reappears. Let's define 1 to theta. So the term is like constant times levert x vert no. What do we know about theta?
Since the KL exponent theta is assumed to be in the interval 12 lover 3, let's see what happens to nu. If theta clef 2, then 112, then 112, 12. If theta approaches $1 from below, then $1 theta approaches dealer, and the theta approaches $1, so nu approaches dealer dollars. So the exponent nu lies in the range 2 Euler's linear.
Okay, so the bound is delvert x's x plus Elbert x per constant is between 0 and 1.
Exactly. Now, if theta were equal to 1, which happens only if theta equals to the PL case, then both terms are linear in Delvert x state, and we recover standard Lipschitz continuity for null x set.
But we established that theta is generally greater than 12 for many interesting non-convex problems.
Right. So in the more general case where Vickers and 12, Baker, the exponent 1 will be strictly less than 1. This means the gradient edible fx lower is not Lipschitz continuous. The change in the gradient can grow faster than linearly when points get very close, governed by that fractional exponent lu. This is the definition of Holder continuity for the gradient.
So Theorem 1 essentially says, thanks to the local KL property holding for the inner lifted problem with exponent theta, the resulting outer maximal function 5x has a gradient that is Holder continuous with exponent theta.
Precisely. This is the crucial theoretical bridge. It translates the geometric property, local KL, of the inner maximization problem into a usable, though weaker than Lipschitz, smoothness property for the outer minimization problem.
And why is establishing any kind of smoothness, even Holder smoothness, so important?
Because it's the key that unlocks the door to designing and analyzing first-order optimization algorithms like proximal gradient methods for the outer loop. Even though we don't have Lipschitz smoothness, Holder smoothness is still enough structure to control the algorithm's step sizes and prove convergence, albeit potentially at a slower rate than in the Lipschitz case. Without Theorem 1, we wouldn't know how to proceed algorithmically for the outer problem.
Got it. The local KL analysis yielded the local Holder smoothness, which is the property the algorithm will exploit. Hashtag tag 2.4, the intuitive example, example 1.
Now, all this talk about local KL versus global KL and lifting might feel a bit abstract. To really drive home why the localized assumption is necessary and powerful, the authors provide example 1. We should definitely spend some time on it.
Okay, example 1. Looking at it, it's a Minx-Maxia problem. The objective involves the term Tho by 2 Sing metal. The variable Singfui is constrained to the interval $1 due. The variable day is constrained by 2 Sambler, where its Singfui involves Anis time nullers, and this auxiliary variable is Singfui appears in the constraint.
Yes, this example is constructed based on the lifted problem formulation directly. So the inner maximization is implicitly over both Yeti and Zolotarnever, subject to constraints. The objective inside the max is 2 pi c, and there's also an indicator function, delta 2 pi 3, effectively constraining to the interval 0, 2, 1. The constraint involves terms like he py plus 2 for some radius trio dollars.
Okay, so it's a somewhat artificial problem designed to illustrate a specific point.
Exactly. It's synthetic, carefully engineered to be a case where global properties fail. But the local KL condition holds, and the theory applies. The authors explicitly show that the lifted function, nel toki, associated with this example, fails to satisfy the KL property globally.
Where does it fail? What's the specific point of failure?
The failure occurs at the point P2 pi 2. Let's analyze what happens there. First, they calculate the subgradient of the inner problem's objective with respect to real z at this point for fixed sigdillers. It turns out that the distance from 0 to this subgradient, partial P2 2, is exactly 0.
Zero gradient, so pi times z dollar looks like a stationary point for the inner problem for fixed x.
It does, based on the gradient information. However, they then calculate the actual optimal value of the inner problem and compare it to the value of the function at this specific point, pi 2 stacks. The difference, the objective gap, turns out to be phi pi 2, pi 2, pi 2.
But $6 is in the interval $1, 2 trips. So $6 is at least 1.
Precisely. The objective gap is positive, strictly greater than 0. In fact, at least 1. So the point is not the optimal solution for the inner problem.
Let's put that together. At PDZ EU221, the subgradient norm is 0, suggesting it's stationary. But the function value is strictly less than the optimal value, meaning it's not optimal. This is exactly the kind of pathological situation KL is supposed to prevent.
It is. If you tried to apply the standard KL inequality here, which fundamentally requires the function gap to be controlled by the subgradient norm, pre-G tech subgradient norm, you'd have a positive value on the left side, related to the gaps in KDO2, and 0 on the right side, the subgradient norm. The inequality is violated. Global KL fails.
Okay, so this example definitively breaks any hope of relying on a global KL condition. How does the local KL condition rescue the situation?
This is where the level set and the parameter sigma become critical. Remember, the local KL condition assumption 1, only needs to hold for points inside, where the gap is bounded above by gamma 6, 0, 0, partial sigma.
Right.
In this specific example, the authors show that it satisfies the local KL condition with parameters 12.2 and 2 under C2, and crucially, sigma dollars.
Sigma, what does that imply for Legel dollars?
With sigma dollars, the upper bound defining Legel becomes gamma Delo.
Like that.
So Legel's Delos is the set where the gap is positive but less than or equal to gamma D.
And the point had a gap of 6 by 102s, which is at least 1.
If Gemelli is chosen appropriately, in exams less than 1, then the pathological point, where the gradient vanished incorrectly, simply falls outside the level set where the KL condition is required to hold.
So the local condition neatly sidesteps the problematic point. It says, we only need the KL property in this region, and that nasty point isn't in this region, so we don't care about it.
Exactly. By restricting the scope of the KL assumption to the dynamically defined local region, the theory remains valid, even in the presence of such pathological points that would break a global assumption. It demonstrates the power and necessity of the localization.
This example really clarifies it. It's not just a theoretical technicality. It directly addresses potential failure modes by focusing the assumption where the algorithm actually operates near convergence.
Precisely. It validates their careful theoretical setup
Okay, we've established the problem, the need for KL theory, the power of the local KL condition on a lifted problem, and how that yields local Holder smoothness for the outer function 5xers. Now, how do we actually build an algorithm that leverages all this? It seems like we need two parts,
Yeah.
something for the inner maximization and something for the outer minimization.
That's exactly right. The overall solution proposed is a nested approach. For the outer minimization over $6, they use a variant of the proximal gradient method, specifically an inexact proximal gradient, IPG method.
Inexact, okay. We'll come back to why it's inexact, but this outer IPG method will need information from the inner problem at each step, right?
Yes. At each iteration, dollars, the outer method, operating on $6, needs to figure out something about the inner maximization problem corresponding to this dollars. Specifically, it needs an approximate solution, Giesebauer Thumber, to the inner problem, the SK, XA, XA,
Huh.
and the gradient dollars, XK, SK, XA.
And solving that inner maximization is hard, as we've discussed. It's non-concave and Gideon has the complex constraints, so how do they handle that?
This is where the second algorithmic component comes in. The sequential convex programming, SCP method. SCP is used as a subroutine within each outer iteration to find that approximate solution, $y for the inner problem.
So the overall flow is outer loop IPG updates $6. To do that, it calls an inner loop, SCP, to approximately solve the maximization for the current $6.
Correct. Let's dive into the SCP method first, algorithm 1, as it handles the core difficulty of the constrained inner maximization. Hashtag tag tags 3.1, the sequential convex programming, SCP method, algorithm 1.
Okay, SCP. The name suggests it uses convex programming somehow, but the inner problem is non-concave and non-convexly constrained. How does SCP bridge that gap?
SCP is an iterative method itself. It tackles a difficult non-convex inner problem by solving a sequence of approximating convex subproblems. At each inner iteration, let's use index dollars for the inner loop, generating points dollars represent the lifted pair from the lifted problem. It constructs and solves a simplified convex optimization problem that's locally accurate around the current point C.
So it linearizes or convexifies the problem locally.
Essentially, yes. Let's look at the subproblem it solves in step 4 of algorithm 1, defined by formula 27. It's trying to find the next inner iterates k plus one other 1. The subproblem involves minimizing a function.
What's in that function?
It has several parts. It includes the simple convex function qz from the original problem. It includes a linearization of the non-concave part of the objective around the current point zeta. And crucially, it includes a quadratic proximal term, Tolfert Tk, where inti is a step-size parameter. This quadratic term keeps the next iterate dk I plus 1 dea close to the current iterate and makes the subproblem strongly convex.
Okay, so the objective function of the subproblem is convexified using linearization and made strongly convex by the proximal term. What about the constraints? The original constraint, or its lifted equivalent, is the hard part.
This is perhaps the most critical part of the SCP approach here. Instead of trying to enforce the original, potentially non-convex constraint directly in the subproblem, SCP uses a surrogate convex constraint. The subproblem requires Zilid to satisfy C-bar.
What is that?
C-bar I is a convex function that approximates the original constraint function in the neighborhood of the current inner iterate dollars. Typically, it might involve a linearization of cell plus perhaps a simple quadratic term to ensure convexity or provide a better local fit. The key is that SE defines a convex feasible region for the subproblem.
So the subproblem, formula 27, is minimize a strongly convex objective subject to convex constraints, LaTeX. That is a convex optimization problem.
Exactly. And convex optimization problems can typically be solved efficiently and reliably, often to high accuracy. So SCP replaces the hard non-convex problem with a sequence of tractable convex problems.
But each convex problem is just an approximation. How do we ensure solving these approximations actually makes progress on the original non-convex inner problem?
That's where the rest of the SCP machinery comes in, particularly the backtracking line search described in step 5. After solving the convex subproblem to get a candidate next point zki plus 1 die, the algorithm checks if this step provides sufficient decrease in the original inner objective function, or a related merit function be day.
What's the condition for sufficient decrease?
It typically requires the actual decrease in the merit function HADI plus 1 to be at least a certain fraction, controlled by a parameter beta of the square distance moved, d of n plus 1, 1022. This ensures we're making meaningful progress relative to the step size.
And if the condition isn't met, if the approximation was poor and we didn't get enough descent?
Then the approximation was too aggressive. The algorithm backtracks. It shrinks the step size parameter of beta, which tightens the proximal term, keeping the next step smaller and closer to the current point where the approximation is more likely to be accurate, and resolves the now modified convex subproblem, 27. This repeats until the sufficient decrease condition is satisfied.
I see. The backtracking ensures that each accepted step of the SCP makes guaranteed progress on the actual non-convex inner problem, even though the steps are generated by solving convex approximations.
Precisely. It provides the necessary safeguard.
And how long does this inner SCP loop run? What's the stopping criterion?
The SCP subroutine, algorithm 1, continues iterating, updating itollers until a specific stopping criterion is met, given by Formula 28. This criterion essentially checks if the current iterate scour, which becomes the output decalers for the outer loop, is sufficiently close to being a stationary point for the lifted inner problem. It measures the norm of a term related to the subgradient of the lifted objective psi at C hours and requires it to be below a certain tolerance to Dollar.
So SCP runs until it finds an approximate stationary point for the inner maximization problem, with accuracy controlled by Caller.
Exactly. It finds a Tau approximate solution.
Now, how does the performance, the speed of this SCP subroutine depend on the problem properties? You mentioned the KL exponent iterator earlier. Does it play a role here?
It plays a crucial role. Theorem 5 in the paper analyzes the convergence rate of the SCP subroutine under the local KL assumption, assumption 1. It provides an upper bound on the number of inner iterations, let's call it K8, needed to reach that Tau approximate solution.
And how does K theta depend on Hata and Tau?
The dependency is quite revealing. If the KL exponent theta happens to be exactly $12.2, which corresponds to the simpler PL condition holding locally, then the number of iterations K theta depends only logarithmically on $1 Tau. This is very fast convergence.
Logarithmic in the inverse tolerance. That's typical for strongly convex or PL settings. What if theta at 12.2?
If theta is in the range, $12, which is the more general non-convex case, the complexity becomes polynomial in $1. Specifically, Theorem 5 shows that theta scales Rabi-like raised to the power 12 theta.
Let's examine that exponent. Let's examine that exponent. TOEFL of 1, if TOEFL is just slightly bigger than 12.2, say the elephant 6 cents, then $2 theta 1 to 1.21, 1.281, and the exponent is $10 to Nutrition is $5. If TOEFL is under 9 cents, then $2 theta 1.81, and exponent 1088 is $1 to 2 or 1.010. The exponent seems to decrease as the theta increases. Let me recheck Theorem 5. It relates the number of outer iterations for SCP, not total complexity. The theorem actually bounds the number of iterations to reach a certain error reduction factor. Let's look at the complexity rate tolerance now. Okay, Theorem 5 actually gives complexity bounds like mathematical all art, depending on the regime. Let's focus on the dependence. As the theta gets closer to 1...
Right, as the theta r approaches 1, meaning the function is getting flatter, closer to the edge of KL applicability, the term 2 theta 1 approaches $1. The exponent also approaches $1. If we look at the other form, 2 theta approaches $1. The exact complexity depends on how TOE relates to the initial error, but the key point is the polynomial dependence on $1, with the exponent explicitly determined by theta.
So, the geometry of the inner problem, captured by the local KL exponent theta, directly dictates the computational effort required by the SCP subroutine to find a solution of a given accuracy tau. A nicer geometry, closer to 12, means faster convergence.
Absolutely. It's not just a theoretical parameter. It has direct algorithmic consequences for the inner loop's efficiency. Hashtag tag 3.2, the inexact proximal gradient IPG method, algorithm 2.
Okay, so we have the SCP engine, algorithm 1, ready to tackle the inner maximization and deliver an approximate solution, EKS, representing the optimal pair with tolerance algorithm. Now let's go back to the outer loop, algorithm 2, the inexact proximal gradient method, which updates the main variable $6.
Right. Algorithm 2 orchestrates the overall process. At each outer iteration dollars, it starts with the current outer iterate $6 and the approximate inner solution AK1 from the previous iteration.
Step 1, start with K1. Got it.
Step 2. Call the SCP subroutine, algorithm 1, to solve the inner maximization problem corresponding to the current scalar. This gives a new approximate inner solution, which we'll call SCA. This GACAN satisfies the SCP stopping criterion with tolerance. The tolerance might change across iterations.
Okay, so SCP finds AXKOY, SKYQY, then what?
Step 3 involves computing the gradient of the original function $5 with respect to $6 evaluated at the current point. XK, Koskala. Let's call this GK nadlax XKYK.
And step 4 is the core update for Sexley. It looks like a proximal gradient step. XK plus 1 is obtained by minimizing something.
Yes. 6K plus 1 is the solution to the minimization problem. XXK wrangle plus first K XKDN2 at XK Let's break this down.
Okay. The first term Langle GK-XXK wrangle is the linear approximation using the gradient GK we just computed. The last term is the simple convex function, like a regularizer or indicator that we always had. The middle term is the quadratic proximal term for XJ2.
Right. This whole expression is a local model of the original outer objective fx plus px, round the point 6k dols. The gradient GK nabla fxk yk serves as an approximation to the true gradient fxky or sub k. Is a step size parameter, analogous to the Lipschitz constant in standard proximal gradient.
Now let's address the inexact part. Why is this method called inexact proximal gradient?
It comes directly from the fact that we're using GK nabla SXK in the update step instead of the true gradient of the maximal function nabla SK.
Why can't we use the true gradient fxk doll?
Because computing nabla FK typically requires knowing the exact solution via the inner maximization problem. Finding this exact solution is often computationally prohibitive, sometimes theoretically impossible in finite time, especially given the non-concavity and constraints.
So SCP only gives us an approximate inner solution, nabls, and we use that dollars to compute our gradient approximation g-dolls. The inexactness comes from using Yalor instead of y.
Precisely.
Sure.
G-dollar is an inexact gradient for the outer objective nabla.
Okay, but this sounds potentially dangerous. We establish phi x is already tricky, only Holder smooth. Now we're feeding its optimization algorithm an inexact gradient. How can we possibly guarantee convergence? Doesn't the error from the inexactness accumulate or throw the algorithm off course?
That is absolutely the core theoretical challenge that the paper needs to address and does address. The key insight, rigorously proven in their analysis, particularly around lemma 10, is that the errors are controllable and linked.
How are they controlled?
It comes back to the local KL property assumed for the inner problem and the stopping criterion used in the SCP subroutine. Because SCP finds a AI color that satisfies the Bleschel talk, the analysis shows that the resulting gradient approximation nablax FSK color is actually close enough to the true gradient XKSK.
Close enough in what sense?
Close enough that the error introduced by using G actors instead of nabla FXK doll is bounded, and, crucially, this error can be made arbitrarily small by choosing the inner loop tolerance talk sufficiently small. The analysis carefully tracks how the inner accuracy talk needs to be tightened as the outer loop progresses, as Kelly increases, to ensure overall convergence.
I see. So the outer loop dictates the required accuracy talk for the inner SCP loop, ensuring the gradient approximation is good enough at each stage.
Exactly. It's a coupled system where the required inner precision depends on the outer progress.
And what about that step size parameter in the $6 update? How is that chosen? Does it relate to the Holder smoothness?
Yes, it absolutely does. Since we know from Theorem 1 that $5 is only Holder smooth, with exponent theta, and not necessarily Lipschitz smooth, we can't just use a fixed step size based on a Lipschitz constant. The parameter talk needs to be chosen carefully, often using a backtracking line search or an adaptive procedure specifically designed to handle the Holder continuity.
So the step size rule is different from standard gradient descent.
It has to be. The update rule and the choice of jailer are designed to guarantee sufficient descent in the outer objective despite both the weaker Holder smoothness and the inexactness of the gradient GDLR. It ensures that the algorithm still makes progress toward an approximate stationary point.
Okay, so putting it all together. ITG algorithm 2 drives the outer minimization for $6. At each step, it calls SCP, algorithm 1, to get an approximate inner maximizer arrow with controlled accuracy talk. It uses our to get an inexact gradient nadir. Then it takes a proximal gradient step using GD$ and a carefully chosen step size adapted for Holder smoothness. The whole process relies on the local KL property, inner translating to local Holder smoothness, outer, and allowing the inexactness to be managed.
That's a perfect summary of the algorithmic machinery. It's a tightly coupled system designed to navigate this complex landscape.
All right, we have the theory, local KL, Holder smoothness, and the algorithm, IPG with SCP subroutine. The crucial question now is, does it work efficiently? What are the complexity guarantees? How many steps, how many gradient calculations does it take to find a solution?
This is where the rubber meets the road theoretically. The paper provides rigorous complexity bounds for the entire IPG-SCP framework to find what they define as an epsilon stationary point.
Okay, epsilon stationary point, we need to define that first. It sounds like it involves two tolerances, epsilon and $3.
It does. It's a slightly more nuanced definition of approximate stationarity than just requiring the gradient norm to be small. Let epsilon be the set of all epsilon stationary points. Points epsilon, epsilon, epsilon. The epsilon stationary point is a point that is within a distance Thor of this set epsilon.
So we need to be close, within radius $1, to a point that is approximately stationary, gradient norms 10 of 1. Why this two-parameter definition?
It arises naturally from the analysis, particularly when dealing with the local conditions and the potential non-smoothness. The radius dollars itself is defined in terms of epsilon and the problem parameters. Specifically, the paper defines that as gamma epsilon sigma divided by $4, where gamma and sigma are from the local KL assumption, and thus sigma is related to the smoothness of the original function far.
Ah, gamma and sigma are back. So the target radius dollar depends directly on the parameters defining the local KL level set. What does that dependency tell us?
If sigma is dollars, then $3 is proportional to gamma. If sigma dollars, then as we demand higher precision, epsilon goes to 0, the target radius dollar shrinks, like epsilon sigma. This means the algorithm needs to get closer and closer to the set of truly epsilon stationary points, and how close is dictated by sigma. It connects the required solution accuracy directly back to the geometric properties assumed via the local KL condition.
Okay, that makes sense. Trilon links the desired precision epsilon to the problem's intrinsic geometry, gamma. Now, what about the complexity to actually find such an epsilon stationary point? Let's start with the iteration complexity theorem 6. This counts the number of outer loop iterations.
Theorem 6 gives the total number of outer IPG iterations required. Ignoring constants and logarithmic factors using the tilde notation, the complexity is shown to be tilde theta 1 sigma theta.
Wow, okay. That exponent is packed with information. It's epsilon raised to a negative power, which means complexity increases as epsilon gets smaller, as expected. But the power itself is the maximum of two terms, $1, and sigma theta.
Yes. This maximum captures the fact that the overall complexity is determined by the bottleneck arising from two different aspects of the problem structure, both related back to the KL parameters theta and sigma theta.
Let's look at the first term in the max. This depends only on the KL exponent theta.
Right. We know theta in $1. If theta is close to $12, like the PL condition, then $1 A theta is close to $12, and the exponent $1 is close to 2. This gives a complexity like tilde on 2, which is common for non-convex optimization under PL-like conditions.
But if theta approaches 1, the function gets very flat near stationary point's weakest KL condition.
Then $1 theta approaches 0 from the positive side, and the exponent $1 theta 1 blows up towards infinity. This reflects the intuitive fact that optimizing functions with worse KL exponents, closer to 1, is fundamentally harder and requires more iterations.
Okay, so that first term captures the difficulty purely from the flatness described by theta. What about the second term, sigma theta? This brings in the shrinking parameter sigma.
This term captures the difficulty related to the locality of the KL condition and how the target region shrinks. Remember, sigma circa controls how fast the level set shrinks as Sixth law approaches stationarity, and also how fast the target radius shrinks with epsilon. A larger sigma implies a more rapidly shrinking target, which can also increase complexity. This term relates that shrinking behavior to the underlying flatness.
So the algorithm's iteration complexity is dictated by whichever of these two factors. The flatness, or the interaction of locality and flatness, is worse, i.e. yields the larger exponent for $1 epsilon.
Exactly. It elegantly summarizes how the core geometric assumptions translate into the final iteration count.
Now, iterations are one thing, but actual computation involved gradient evaluations, especially within that SCP inner loop. Theorem 7 addresses the first-order oracle complexity, right? The total number of gradient calls.
Yes. Theorem 7 provides the bound on the total number of gradient evaluations needed. Specifically, calls to the metal 4 and potentially another go. This is arguably a more practical measure of complexity. As you'd expect, it's higher than the iteration complexity because each outer iteration requires running the SCP subroutine, which itself performs multiple gradient evaluations.
How much higher? How does the formula change?
The formula gets more complicated naturally. It essentially involves multiplying the outer iteration complexity from Theorem 6 by the complexity of the inner SCP loop, related to Theorem 5. When theta in 12, $1, the resulting exponent on epsilon dollar becomes something like epsilon raised to the power of theta times max theta stay.
Looking at the paper, something involving theta looks like 2 theta plus 1 times the exponent from Theorem 6. It's quite complex.
It is complex, but the crucial takeaway is not the exact form of the exponent, but the fact that it remains polynomial in $1 epsilon. Even though we have a nested loop structure, non-convexity, non-concavity, complex constraints, and inexactness, the total number of gradient calls required is still bounded by a polynomial function of the desired precision $1 epsilon.
That's the key validation, isn't it? For this incredibly difficult class of problems where you might worry about exponential complexity or lack of guarantees, they've established a first-order method relying only on gradient information that provably converges with a manageable polynomial number of oracle calls.
Precisely. It confirms the theoretical efficiency and soundness of the entire IPG-SCP framework. It's a significant theoretical achievement for this problem class. Hashtag 4.2 preliminary numerical results.
Theory is crucial. Complexity bounds are essential proofs of concept. But, the audience always wants to know, does it actually work in practice? Did the authors run any experiments?
They did include some preliminary numerical results to demonstrate the algorithm's behavior on a challenging test case. They formulated a specific constrained Minimax problem, labeled Problem 43.
What does Problem 43 look like? Is it designed to test the difficult aspects?
Yes, it seems specifically constructed for that purpose. The objective function involves the Hadamard product, element-wise product, of vectors related to 6 an hour. More importantly, the inner constraint function for its y involves complex exponential terms, like ncjyj plus ikij.
Exponential constraints. That sounds non-convex and potentially tricky to handle.
It definitely ensures the inner problem is non-trivial and fits the paper's targeted problem class. Non-convex, non-concave objective with non-convex inner constraints.
Okay, so they tested their IPG-SCP algorithm 2 on this problem 43. What did they measure? Let's look at Table 1.
Table 1 shows results for different problem dimensions, specifically the dimensions of the outer variable $n and the inner variable $. For each instance, they report several values. Key ones are the initial objective value, the final objective value found by their algorithm, and importantly, 2 versions of this final value.
2 versions. What's the difference?
They report the approximate final value and the actual final value. The approximate final value is calculated using the final outer iterate $epsilon and the corresponding approximate inner solution $y that the SCP subroutine produced in the last step. So it's catalon, approxilon, y-epsilon plus p-epsilon, ky-epsilon.
Okay, that's the value the algorithm itself sees. What's the actual final value?
To get the actual final value, they take the final outer solution, epsilon, found by their algorithm, and then they use a separate high-precision global solver to find the true optimal inner solution corresponding to that epsilon. The actual final value is then epsilon plus p-epsilon calculated using this true y-epsilon.
Ah, I see. This comparison directly tests how good the approximate inner solution y-epsilon produced by SCP really is. If the approximate and actual final values are close, it means SCP did a good job finding something near the true inner maximum.
Exactly. It's a sanity check on the practical impact of the inexactness we discussed.
So what do the numbers show? Let's take an example. Say 1 150 and 2 is $500. The initial objective value is around 0.5. The algorithm drives it down significantly. The actual final value is reported as 164.92.
And the approximate final value, calculated using the algorithm's own epsilon, is negative $165.09.
Wow, those are extremely close. A difference of only about 0.17 on a value of negative 165.
Yes, and look at the next instance, $160 and $260. Our actual is negative 279.51. Approximate is negative 279.53. Again, virtually identical. The pattern holds across the different dimensions reported.
That's quite compelling empirical evidence. It strongly suggests that the SCP subroutine, despite only finding a tap approximate solution y-epsilon for the inner problem, is finding a point that is, for practical purposes, yielding nearly the same objective value as the true, globally optimal inner solution yay, ace epsilon.
It validates the whole concept of controlled inexactness. The theory guaranteed that the errors could be managed, and these results show that in practice, the final approximate solution, the epsilon, is indeed very close to the true maximizer set, yay epsilon, in terms of the objective value achieved.
So the practical takeaway from the numerics is that the IPG-SCP framework isn't just theoretically sound with polynomial complexity, but it also appears robust in practice, capable of handling these high-dimensional, non-convex, constrained problems and delivering solutions that are effectively achieving the true Minimax objective value.
That seems to be the clear message from these preliminary results. It builds confidence that the approach is viable beyond just the theory. Hashtag tag outro.
Well, this has been a genuinely deep dive. We've really unpacked the layers here. I think the core takeaway for me is how this work represents a significant step forward in handling these really tough, constrained Minimax problems. The breakthrough isn't just one single trick, but rather this cohesive 3-part strategy.
I agree. It's the combination. First, the cleverness of lifting the problem to handle the implicit inner constraints. Second, the crucial theoretical insight to use the KL condition locally on that lifted problem, avoiding the overly strong global assumptions. And third, implementing that theory with a practical SCP engine that uses sequential convex approximations to navigate the non-convex inner landscape.
And that SCP part, using the convex surrogate constraint collar, seems absolutely vital for making the inner loop tractable.
It is. That's the algorithmic engine. But as we discussed, the justification for why that engine works and why the inexactness it introduces doesn't break the outer loop relies entirely on that rigorous local KL analysis, which delivered the local holder smoothness property for the outer function. It's the interplay between the local geometry, KL, and the algorithmic approximation, SCP, that makes it all hold together.
It really feels like a template, doesn't it? This idea of not demanding impossible global properties, but instead proving strong local behavior using tools like KL and then carefully designing algorithms that exploit that local structure, even with approximations. That seems like a powerful paradigm for tackling other complex, non-convex problems.
Absolutely. It's about finding the right assumptions that are weak enough to hold for realistic problems, yet strong enough to provide theoretical guarantees for practical algorithms. The local KL condition, especially when combined with techniques like lifting or penalty methods, seems to hit that sweet spot for many challenging optimization settings.
Which, naturally, leads to a final thought, a question perhaps for you, the listener, especially if you're working in areas grappling with complex constraints. If we connect this strategy, this careful blend of lifting, local condition analysis, and sequential approximation to the bigger picture, say in AI, how might these ideas be adapted?
For instance,
Well, think about areas like safe reinforcement learning. You often have complex, maybe non-convex constraints on the agent's actions or states for safety reasons. Or consider constrained GANs, where you might want the generator to satisfy certain properties, imposing constraints on the adversarial game. Could similar strategies of analyzing local conditions on potentially lifted or penalized versions of these problems lead to more rigorous and provably convergent algorithms in those domains?
that's a fascinating direction. Applying this level of rigorous complexity analysis, born from optimization theory, to define and solve constrained objectives in areas like AI safety or robust generation, that seems like a very promising avenue for future work, bridging that gap between the mathematical rigor we've discussed today and the practical needs of complex, constrained AI systems.
Definitely food for thought. It highlights how fundamental advances in optimization theory can ripple outwards. Well, thank you for joining us on this incredibly detailed exploration of the constrained non-concave Minimax landscape. It was quite the journey.
Indeed, a challenging but rewarding topic. Until next time. Welcome back to the Deep Dive. Today, we are really strapping in. We're embarking on an extremely granular tour of some pretty advanced optimization theory.
Yeah, this isn't going to be a high-level summary. We're planning a full walkthrough.
Exactly. Sentence by sentence, formula by formula. We're breaking down every critical mathematical choice the authors made in this paper.
And, it's necessary because the problem itself is, well, it's structurally one of the most complex you find in modern machine learning, or game theory.
Right. What's the formal title again?
It's a first-order method for constrained non-convex-nonconcave minimax problems under a local Kurdyka-Łojasiewicz condition. Quite a mouthful.
It really is. And our mission, our goal here, is to take this dense paper, this, stack of definitions and formulas, and really extract the functional knowledge.
So by the end of this deep dive, you, the listener, won't just know what they proved.
Hopefully you'll understand the why behind it, the deep mathematical structure, the compromises they had to make to get these results.
Let's dive in. Okay, so first things first. The foundational object. It's problem 1 in the paper. This formula, it's really the concise definition of the specific type of constrained minimax problem we're tackling.
All right, let's put it under the microscope then. Formula 1, it reads, the minimization over x of the maximization subject to the constraint c of y is less than or equal to 0 of the expression f of x, y, plus p of x minus q of y.
So structurally, it's nested. Minimize, then maximize.
Exactly. Think of it like maybe a zero-sum game, or perhaps adversarial learning. You have 2 players, essentially.
An outer player, x, trying to minimize the outcome.
Right. Get the lowest score possible. And an inner player, y, who's trying to maximize it,
Yeah.
get the highest score. And these x and y, They're vectors living in their respective spaces, say Rn1 and Rn2.
Now the objective function, fxy. The authors state it's smooth, but here's the kicker. Potentially non-convex in x and non-concave in y. And that's the core difficulty, isn't it? That immediately throws out, well, most standard convex optimization techniques.
Right. If O were convex-concave, things would be much simpler. We have saddle point theorems, uniqueness maybe.
Precisely. But non-convex-nonconcave means we're dealing with a much more complicated landscape. We could have saddle points that aren't global optima, the surface is rugged, convergence becomes significantly harder to guarantee.
Okay, so F is the complex part. What about P, X, and Q? They're called simple closed convex functions. What does simple mean here, practically?
Simple is a technical term here. It usually means that while these functions might add non-smoothness, think like an L1 norm penalty or maybe an indicator function for a simple set, we can handle them efficiently.
How?
Typically using their proximal operators. So the complexity isn't really in P and Q themselves, it's pushed onto the smooth part, F, and crucially, the constraint structure, C.
Yeah, the constraint C of Y less than or equal to 0. That's the final piece. It means the maximizing player, Y, can't just choose any value.
Right. They have to operate within a feasible set, let's call it S. And this set S is defined by this smooth mapping C. It's not necessarily a simple box constraint or anything like that.
It could be a complicated nonlinear boundary.
It could be, yeah. So the intuition, the overall picture is player X makes a move, chooses a strategy. Then, knowing X's move, player Y reacts.
By finding the best possible counter strategy.
The one that maximizes the outcome, but it has to be feasible. It has to satisfy C of Y less than or equal to 0.
And then X, knowing how Y will react optimally, makes the initial choice that leads to the best possible outcome for itself, which means minimizing that maximal value.
That's the essence of this constrained Minimax setup.
Okay, so why focus specifically on this problem? 1, the paper mentions a more general problem too, which also has constraints on X, the minimizer. Why not tackle that directly?
That's a good question. The connection is through something called the penalty approach. It turns out that solving the more general problem, the one with constraints on both X and Y,
which is Fx plus Px.
Right, that one. Solving that actually relies directly on being able to solve a sequence of subproblems that look exactly like problem 1.
How does that work? How do you handle the outer constraint, d of x less than or equal to 0?
The standard way is to, well, you fold it into the objective using a penalty term, usually a quadratic penalty.
So you'd add something like rho times the norm squared of the positive part of dx.
Exactly. You create a sequence of penalized problems, minimize over x, maximize over y, subject to c of y less than or equal to 0 of the original objective plus this penalty term, dx plus 2, 2.
Where rho k is the penalty coefficient, and you let it increase, potentially go to infinity.
Right. And notice that penalty term plus 2, 2, it only depends on x.
So it just gets absorbed into the outer minimization part. It combines with fx, y, and px.
Precisely. So the structure remains minimize something over x, maximize something over a constrained y, which is exactly the form of problem 1.
Okay, so problem 1 is really the fundamental building block needed to solve the more general case. That makes sense.
Yeah, it confirms its importance.
So if it's that fundamental, why is this paper needed? What makes this problem so hard that prior methods couldn't handle it? What's the gap?
Well, the vast majority of prior work, especially in the non-concave setting, focused on the unconstrained inner problem.
You mean problem 3 from the paper plus px, by?
Yeah.
No constraint on y.
Exactly. In that unconstrained world, researchers could leverage some powerful assumptions to guarantee convergence. Things like the Kurdyka-Łojasiewicz condition, the PL condition.
Right, the PL condition, that's a big one. It's weaker than assuming strong convexity or concavity, but it still gives you a handle on convergence rates, even when things aren't convex.
It does. And interestingly, the PL condition is actually a special case of a more general condition called the Kurdyka-Łojasiewicz condition, or KL condition. Specifically, PL is KL when the KL exponent, which we'll call theta, is 1/2.
Okay, so KL is more general than PL. But what breaks when we add the constraint COAY? 0.
The constraint fundamentally changes the geometry of the space player Y operates in. Those nice assumptions like PL or even global KL conditions used in some prior work, they often rely on the structure of the unconstrained space. Introducing a complex, possibly nonlinear constraint boundary just, well, it breaks those assumptions.
So existing algorithms designed for the unconstrained case just don't apply here.
Largely, no. They don't handle the constraint properly. And that's the critical gap this paper aims to fill, tackling the constrained inner maximization counterpart.
Okay, so let's outline their approach, the main contributions they list. First, there's a conceptual breakthrough, right? Establishing some kind of smoothness for the outer player's objective.
Yes, for the maximal function, which they call fev exta, that's the value player y achieves for a given x, its bearer y. They establish local holder smoothness for this function.
Which is weaker than standard Lipschitz smoothness, but still very useful.
Very. And the way they achieve this is key. They impose a local KL condition, but not directly on the original inner problem f.
They impose it on this lifted Minimax problem they introduced.
Exactly. This lifting technique is probably the core mathematical innovation here. We'll definitely need to unpack that later.
Okay, so that's contribution one, local holder smoothness via local KL on a lifted problem. What's second?
Second is the algorithmic contribution for the inner problem. They propose a specific method called sequential convex programming, or SCP. That's algorithm one.
And this SCP method is designed specifically to handle that constrained subproblem, maximizing over y.
Yes. And they prove it converges, crucially, under that local KL assumption they made on the lifted problem.
Got it. Then third.
Third, they embed this SCP solver within a higher-level algorithm for the outer minimization over x. They use an inexact proximal gradient method, or IPG, that's algorithm 2.
Why inexact?
Because solving the inner maximization exactly at every step of the outer algorithm would be computationally prohibitive. The IPG method only needs an approximate solution from the inner SCP solver.
So it's a nested structure. IPG calls SCP as a subroutine.
Precisely. It's a complex architecture, but it's necessary to handle the fact that full cupping oscillators are non-smooth and expensive to evaluate exactly.
And finally, the fourth contribution. The quantitative results.
Right. The payoff. They establish explicit closed-form complexity guarantees. Both iteration complexity, how many outer steps does IPG take, and first-order oracle complexity, how many gradient computations in total.
And these guarantees depend directly on the parameters from the KL condition.
Yes, specifically on the KL exponent theta culto and another parameter sigma related to the locality of the condition. This provides a rigorous, predictable understanding of how fast the algorithm converges depending on the properties of the problem.
Okay, before we dive deeper into the lifting and the algorithms, we probably need to establish some common language. Given our audience, we can likely skip basics like Rn for n-dimensional Euclidean space or standard norms.
Agreed. Let's focus on the tools needed specifically for non-smooth constrained optimization, which are central here, starting with normal cones.
Right. The paper mentions NSX-dual, the limiting normal cone, and NSX-dual, the regular normal cone. Why are these important?
They describe the local geometry of the feasible set S, especially at boundary points. In standard unconstrained optimization, you look for points where the gradient is 0.
But with constraints, the condition changes. Stationarity means the negative gradient points outwards from the feasible set, or it's 0 if you're in the interior.
Exactly. Mathematically, it means the negative gradient must lie within the normal cone NSXS at a solution X.
Okay, so cones handle geometry. Now, for the functions themselves, especially non-smooth ones like P and Q or the overall objective tangents, we need calculus tools beyond gradients.
Right, we need subdifferentials. First, functions need to be proper domain isn't empty and closed, basically, lower semi-continuous. Then we define the subdifferential.
The paper defines two. The regular subdifferential partially acts on the limiting subdifferential. Partial sets what's the difference and why use the limiting one.
The regular subdifferential, partial hast, is sort of the most intuitive generalization of the gradient. It's the set of vectors, slopes, if you will, that defines supporting hyperplanes to the function's graph at x.
Geometrically, it captures the local downward slopes.
Yes, but the problem is it can be mathematically fragile. For complex functions or at sharp corners or boundaries, the regular subdifferential might be empty, or just the 0 vector, even when the function isn't locally flat.
It doesn't capture enough information sometimes.
Right. The limiting subdifferential, partial phi, is more robust. It's defined as the set of all possible limits of regular subgradients coming from point 6 color that converge to 6 law, provided the function values also converge to phi.
So it considers the limiting behavior of slopes from nearby points where the function might be better behaved.
Exactly. It has better closure properties and provides a more stable definition of stationarity, especially for the kinds of composite, potentially non-smooth functions we see in algorithm 2. That's why it's the standard in modern variational analysis.
Okay, limiting subdifferential, got it. Then there's the concept of slopes, formulas 4 and 5. These seem directly linked to the KL condition. What's the idea behind the slope in Formula 4?
It's defined as a limit superior. Specifically, limits the quantity plus alls.
Let's break that down. Themis phi is the function value difference. The superscript plus alls means take the positive part, Hatta's text difference.
Right. So we only care about direction z, where the function value decreases as you move from z to x.
And we divide by the distance sexty, so it's measuring a rate of change.
It's essentially the maximum instantaneous rate of decrease of the function of velocity at the point x.
Okay, and then Formula 5 defines the limiting slope. Also denoted the xd is using a limit inferior.
Yes, it's the limit of the regular slopes as Zhang approaches also $6 along the function graph, meaning phi02.
Why this limiting version?
Again, robustness and a crucial connection to the subdifferential. For convex functions elliptis, this limiting slope simplifies nicely. It becomes equal to the distance from the origin to the limiting subdifferential set.
So implicit is convex 0, does 6 for convex 6.
Precisely. And since the KL condition is often stated in terms of these slopes, this connection allows us to relate KL to the subgradient norm, which is something more algorithmically tangible, especially for the convex components P and Q.
Makes sense. Finally, definition 1. The target for our algorithm. We're not looking for an exact stationary point, but an epsilon desist stationary point. What does that mean?
It's a practical definition of success for inexact algorithms in non-convex settings. First, define sex-XML as limits of the set of all points x where the limiting slope is small, specifically text litibex partial Latexr. These are the approximate stationary points.
So points where the function is almost flat in some generalized sense.
Yeah.
Right. An epsilon stationary point is then simply a point 6 dollars, which is close to this set sexalon. Specifically, the distance from $6 to the set sexalon text epsilon must be less than or equal to $.
So we don't need our final iterate sextuller to have a small subgradient itself. We just need it to be within distance dollars of some point that has an epsilon small subgradient.
Exactly. It acknowledges that the algorithm might oscillate or terminate slightly away from the true near stationary region, but guarantees we're in the right vicinity.
All right, let's get to the core mechanism of the paper. This lifted problem. First, just a quick recap of the main functions defined in 6 through 9.
Sure. We have 6 system, P key, and Q, the domains. S is the feasible set for Y. SEI is diameter of Y. Evian is the diameter of Y. MUSI measures bounded variation of Q, standard setup stuff.
Then, FEBIOSY is the inner objective for the maximization, including the constraint. FEBIOC, where DD&R is the indicator function, 0 if feasible, infinity otherwise. Phi x is the maximum value of phi xy over y. So phi x is the set of optimal y's that achieve that maximum for a given x.
And finally is the overall function we want to minimize. Phi x plus px, ps, it notes its minimum value.
Okay, standard definitions. Now the innovation, the lifted minimax problem given in pen.
Let's read it. TFC AKSK plus px y.
Okay, notice the changes. We still minimize over x, we still maximize over y, but now there's an additional maximization variable, z, also constrained to be in y via the indicator function at delta y.
And crucially, the original constraint is replaced by a new constraint, delta y.
This is the lifting. We've introduced this auxiliary variable z, which lives in the same space as y, and use it to define a new surrogate constraint function.
What's the motivation? Why add complexity with this extra variable z?
It seems counterintuitive, right? Adding variables usually makes problems harder. But here, it's a strategic move to simplify the constraint structure. How does Barrow-Wilkins simplify things? Let's look at Formula 11, which defines its components Barrow.
Okay, barrel way is a ZL ways defined as Darrell YZ, my YZ wrangle, plus frackle CZL, YZ wrangle, plus frac ol ZD.
Let's parse that. Darrow Z is the original constraint value at Z. YZ wrangle is the first-order Taylor term around Z, and frackle Z is a quadratic term.
Right. If you remember Taylor's theorem for smooth functions, this barrel way, Barrow, is essentially a quadratic upper bound on the original constraint function, CJY, assuming CJY is a smooth.
So Barrow ZYZ for all YZ.
Exactly. Now think about the constraint. For each component J, this inequality well-array ranges to basically say that Y must lie within a certain Euclidean ball centered around CJYZ.
Ah, I see. So the feasible region defined by a Barrow-Z-Linot is the intersection of several Euclidean balls.
Precisely. And optimizing over intersections of balls is generally much, much easier computationally than optimizing over a region defined by arbitrary nonlinear inequalities.
So the lifting trades the complex original constraint for this simpler,
albeit higher dimensional constraint or TROG, it makes the inner maximization subproblem tractable.
That's the core idea. It's a very clever reformulation. They introduce corresponding lifted functions, x, y, z, and GORES dx, based on this new structure.
And critically, the paper claims this lifted problem is actually equivalent to the original one.
Yes. Lemma 3 establishes that maxi xyz xyz es, which means the outer objectives are also identical.
So solving the lifted problem, 10 or 14, is the same as solving the original problem 1.
Correct. And this equivalence is crucial because it allows them to apply their main theoretical tool, the local KL condition, to the lifted function borrow ds, which has this nicer constraint structure, and have the results carry over to the original difficult problem.
Okay, this seems like the right time to dig into the core assumptions, particularly assumption 1, which bundles everything together. Let's quickly go through parts I to 3.
Sure. Part Y is about smoothness of F. It needs to be Lipschitz continuous on some domain omega, and its gradient ADIG4 needs to be Lipschitz continuous, i.e. F is smooth, on omega times Y Euler. Standard stuff for gradient-based methods.
Part 2 covers P and Q. Proper, closed, convex. Proximal operators are easy to compute, and crucially, the domain of QY must be compact, closed, and bounded. And Q has bounded variation 1Y.
Compactness of Y is important. It guarantees the inner maximum is attained.
Part 3 requires the constraint function CCJJ to be smooth, and actually twice continuously differentiable on Y, needed for the quadratic approximation ID.
Right. All fairly standard regularity conditions so far. But then we get to part 4. This is the heart of it. The local Kurdyka-Łojasiewicz condition on the lifted function barfeth.
This is inequality 15. Let's try to say it carefully. For certain x, y, z, it says, c of partial y, z, x, y, z at 8.
Okay, let's unpack that. C is a positive constant. Theo is the KL exponent between 12 and 1, inclusive of 12, exclusive of 1. 1x is the optimal value of the lifted inner problem for fixed x.
Yeah.
Det ISZ is the value at a specific yz.
So the term in parentheses, bar x, there x, y, z, is the optimality gap for the inner problem. How far are we from the max value?
Exactly. The right-hand side is text of dello expes opposi obo. That's the distance from the origin to the limiting subdifferential of bar with respect to the maximization variables y and z.
Which, as we discussed, measures how close yz is being a stationary point for the inner maximization problem.
Right. So the inequality relates the function value gap to the subgradient norm. If the gap is small, we're close to the optimal value, the subgradient norm must also be proportionally small. We're close to being stationary.
It's a kind of geometric growth condition around the maximizers.
Precisely. And the exponent, the theta, controls how sharp that growth is. Theta 12.2 corresponds to quadratic growth, like the PL condition, which leads to faster convergence. As theta approaches 1, the growth becomes weaker and convergence slows down.
But crucially, this isn't assumed to hold everywhere. It's a local KL condition. Where does it need to hold?
It only needs to hold for YZ pairs that fall within a specific level set, denoted in Formula 16.
It only defined as the set of YZ pairs where the optimality gap is positive but bounded. $0 x, y, z, ECO Techist.
Partial bar is sigma. Okay, let's break down that upper bound. Gamma is some positive constant. Sigma is another non-negative constant. And Texit's-Darrow, partial ball is the distance to stationarity for the overall outer problem.
So the region in the X where the KL property must hold depends on how close the outer variable x is to being stationary.
Yes, if sigma dollars as x gets closer to a stationary point of dollar, partial gets smaller. If sigma dollar, the upper bound gamma also gets smaller.
Meaning the level set potentially shrinks as we approach a solution for x.
Exactly. This localization, especially the shrinking effect when sigma dollars, is vital. Assuming a KL condition holds uniformly, even in a fixed neighborhood, is often too strong for these kinds of constrained non-convex problems. This adaptive locality is necessary.
Remark 1 discusses this, saying global KL is too restrictive. And example 1 demonstrates it.
Right. Let's look at example 1 briefly. It's file amational amazo or pile 2, pile f700, file at x3x, relevant 2af, delta ball says at a delta 1, and sickle 1 and creator tells y. X, Pytel is letter y's, y solo.
They show that if you analyze the lifted problem at the point YLZ, your pi 2 high, the KL inequality 15 fails.
Why? Let's trace it. At Tayal Saiho, is the lifted constraint satisfied?
Yes, they show pi 2 high is negative, so it's strictly feasible for the lifted inner problem. Okay, what about the right-hand side of the KL inequality, the subgradient distance?
At pi 2s, pi 2 backs the partial subdifferential, partial pi 2 turns out to be exactly the zero vector, zero literal, so the distance is that.
Left-hand side.
The function gap?
The optimal value R2 is achieved at Y2, and the value bar off is by 2 off is 0. So the gap is sex $2. Since sex dollars is 1, 2 sex dollars is least 1.
So the KL inequality becomes 6 by 2 Fiddler.
Right. But sigil dollars is positive, $6 is positive, the little is in 12, 1. So the left side is strictly positive. A positive number cannot be less than or equal to 0.
So the KL condition fails at pi 2 off 2. It doesn't hold globally or even in a fixed neighborhood containing pi 2 depth.
Correct, but then they argue that the local KL condition does hold. It holds on the level set LX defined by $0 bar tau epsilon sigma. In their specific setup for this example, they use sigma dollars and gamma 18, so the level set requires $0, 18, which translates to the condition 0 by 2, but 2 xins. This excludes the problematic point Y22. They show that on this restricted set, the KL condition holds with theta 12.2 and some constant c.
So the failure point is neatly carved out by the definition of the local level set, 2D.
Exactly. It shows the power and necessity of the local formulation. You only need the property to hold where the algorithm is actually expected to operate as it converges. And the parameters theta and sigma that define this local region directly impact the final complexity bounds.
Okay, so we have this local KL assumption on the lifted problem, bar x. Now, what properties does this bias for the original problem, particularly for the maximal function ES poor?
First, lemma 3 and remark 4 just reiterate the equivalence we discussed. Maxi xy, zxy, zcia xyz, which means bar x. The problems are identical from the outer minimizer's perspective.
And if Yatla is an optimal solution for the original inner problem, then Ni dollar is an optimal solution for the lifted inner problem.
Right. Now, Theorem 1 leverages the local KL assumption to say something strong about fingeness. It states that fingeness is differentiable on a certain set 1 epsilon.
Epsilon is the set of points x where the overall objective epsilon is not yet epsilon stationary, i.e. texel epsilon. So, away from the solution set.
Correct. On this set, fingeness is differentiable, and its gradient is what you might expect from the envelope theorem. Nabla fx, where is any maximizer from 1xy.
So the gradient of the max function is just the partial gradient of f with respect to x, evaluated at an optimal y. That's intuitive.
It is, but proving it rigorously in this constrained non-convex, non-concave setting requires the machinery they built, including the KL assumption.
But the more significant part of Theorem 1 seems to be the bound on the gradient difference, the Holder smoothness in equation 18.
Yes, it bounds the norm of the difference between gradients at 2 nearby points, x and x.
Yeah.
The bound has 2 terms. Let's look at them. The first term is lamella. This is just the standard smoothness inherited from f itself. If dollars were fully smooth, this might be the only term.
But there's the second term, $1 theta theta, C1 theta. This looks more complicated.
It is. Notice the exponent on theta. It's $1 theta, since theta is in 12, theta is in the range dollars.
So if theta 12.2, the exponent is 12 and below 1. In that case, both terms scale linearly with theta thetas, and we get standard Lipschitz smoothness for nabla theta.
Correct. But if theta 12.2, say theta $34, the exponent becomes $34 equals 13.3. Since the exponent is less than 1, this term grows slower than linear. This is characteristic of Holder continuity, not Lipschitz continuity.
So the KL exponent theta directly dictates the degree of smoothness of the maximal function dollars. It's Lipschitz only if the theta 12.2, the PL case. Otherwise, it's only Holder smooth.
Exactly, and this Holder property, with its exponent depending on theta, is fundamental. It governs how large the steps for the outer algorithm, algorithm 2, can be while maintaining stability.
Okay, that's smoothness of data. Theorem 2 gives a related property, a local growth condition for the original inner function theta x.
Yes, equation 19. It essentially translates the KL property assumed on the lifted dollar back to the original dollars. It says that for y values within the corresponding local level set, the optimality gap theta x provides a lower bound on the distance from y to the set of optimal solutions yx.
Specifically, phi xyx is greater than or equal to some constant times raised to the power $1 1 theta.
Right. This confirms that the KL property holds in a slightly different form for the original inner problem too, at least locally. It means if the function value 5xy is close to the optimum x, then y must be close to the set of optimizers x. This is crucial for arguing that the inexact solutions found by the inner solver are meaningful.
Now, before we get to the algorithms themselves, there's assumption 2. The Mangasarian from of its constraint qualification, MFCQ. Why is this needed?
MFCQ is a standard regularity condition used in constrained optimization. It ensures the constraints are well behaved at the boundary.
What does it require?
For any feasible point Jaller in the set S, where tilde j Waller, there must exist a direction tilde j y, where tilde is also feasible in the domain y, such that this direction points strictly inward from all the constraints that are currently active or binding at y.
Mathematically, the directional derivative Langle-Nabel tilde angle must be strictly negative for all Jailers where tilde jy work.
Correct. Think of it as requiring that the feasible region doesn't have sharp outward pointing cusps. There's always a way to step slightly inwards.
And why is this important here?
It's primarily needed to guarantee that the Lagrange multipliers associated with the constraints are well-defined and, more importantly, bounded.
Boundedness of multipliers. That sounds important for numerical stability and convergence proofs?
It is absolutely essential, especially for the analysis of the SCP method, algorithm 1, which explicitly computes or uses these multipliers. If MFCQ fails, the multipliers could theoretically go to infinity and the whole analysis collapses.
And Theorem 3 seems to be the direct payoff from assuming MFCQ. It concerns the lifted constraint as arbal.
Yes. Theorem 3 states that under assumptions 1 and 2, which includes MFCQ, there exists a uniform positive constant zeta such that for any feasible point z in the original constraint set S, we can find a point y in the domain y satisfying the lifted constraint with a strict negative margin.
So for any valid center z for the quadratic approximation, there's always a point y that satisfies the approximate constraint with room to spare, and that room is uniform.
Exactly. This uniform Slater-type condition for the lifted constraint z-lur is a powerful consequence of MFCQ on the original constraints slur.
Let's briefly look at the proof structure for Theorem 3. It seems to use a proof by contradiction.
It does. It assumes the conclusion fails, meaning you can find sequences z-alco and z of z, where z is feasible, such that for all y and y, at least one component for z's alloy is greater than zeta.
Taking the limit as $y, this implies that for the limit point z, we must have $$ for all y in y.
Then they argue that this implies the original constraint must be active at z, i.e. cjz is z.
Now MFCQ, assumption 2, comes in. Since data geobausa MFCQ guarantees the existence of an inward-pointing direction, tilde.
Using this direction, they construct a path z plus t for small positive t. Because tilde z points strictly inwards, they can show that for small enough t, the quadratic approximation LAZ must become strictly negative.
But this contradicts the earlier deduction that z is c for all y and y.
Right. The contradiction establishes the theorem. The existence of that uniform margins of zeta dollars is proven, and this zeta dollar will play a critical role in bounding the Lagrange multipliers in the SCP algorithm.
Okay, let's move on to algorithm 1, the sequential convex programming method. This is the subroutine used to solve the inner maximization problem.
Well, technically, it's presented as solving a generic minimization problem, 24, ECZZ. But yes, in the main algorithm 2, it will be used to solve the inner maximization by setting GMF XY and DIA XY, turning the max into a min.
Got it. So GL is smooth, teeters is simple convex, and FUPA defines the constraints. And assumption 3 requires that the lifted version of this $$ function satisfies the local KL condition, 25, near the optimum dollars.
Yes, the same KL structure we saw before, now applied to the function $, that SCP is minimizing.
What's the core strategy of SCP? How does it work?
It's an iterative method. At each outer iteration k, it uses the current point stick fail to build a simpler approximation of the problem and solves that approximation to get the next potential point.
The approximation is solved in the inner loop, lines 3 to 9. And the key step is line 4, solving subproblem 27.
Right. Subproblem 27 is zk plus 1, and mens monogl plus L is zk plus 1 L that's in subject to the lifted constraint.
Okay, let's dissect this subproblem. The objective is linearizing the smooth part around zk, adding a quadratic proximal term zk with adaptive weight Dallas, and keeping the simple convex part q.
It's essentially minimizing a convex quadratic surrogate for zk plus the simple q.
And the constraint is as zk. We already established this means zk must lie in an intersection of Euclidean balls centered near zk.
Correct. So subproblem 27 is a convex optimization problem with relatively simple constraints. It should be efficiently solvable.
Then line 5 performs a line search, or rather a check for sufficient decrease.
Yes, it checks if the candidate point zk plus 1 also provides enough decrease in the original objective dollars. Specifically, ck plus 1 I as is some constant between 0 and 1.
If the decrease isn't sufficient, the inner loop, indexed by I, increases the quadratic weight LKI and resolves the subproblem. This makes the step COK plus 1 ONG smaller,
eventually ensuring the condition holds.
Right. Theorem 4i guarantees this inner loop terminates finitely. And importantly, the resulting point LK plus 1 is guaranteed to be feasible for the original constraints, LECBL, because LEC plus 1, and the subproblem enforce LEC.
Theorem 4 also says the weights like stay bounded. And it gives the Karush-Kuhn-Tucker, KKT, conditions, 3031, that must hold at the solution ZK plus 1 of the subproblem, with associated Lagrange multipliers lambda.
These KKT conditions are crucial. They relate the gradient nabla, GK, the subgradient of Q, the step direction, and the gradients of the active constraints via the multipliers lambda. They essentially define what stationarity means for this constrained subproblem.
Now, about those multipliers lambda, lemma 1 seems incredibly important. It provides a uniform bound on their L1 norm.
Yes, lambda 1 lay, where A is a constant given by 1 as gay, G dui plus barrel plus MQ.
Let's unpack that constant A. The $ME is an upper bound on the gradient norm, datable G pli A, is the diameter of the domain. Marl is an upper bound on the weights, deletal A, and counts the variation of Q. And crucially, the zeta is the positive constant from Theorem 3.
That's the key dependency. The bound A exists and is uniform because zeta is uniformly positive, which in turn relied on the MFCQ assumption 2.
So MFCQ positive zeta bounded Lagrange. Multipliers lambda. Why is this uniform bound A so vital?
Because the convergence analysis of SCP, particularly relating the step size plus 1 ZC to the distance to stationarity, involves terms that depend on these multipliers. If they weren't uniformly bounded, the analysis would fail. Lemma 8 shows this dependency explicitly via the constant omega in $33.
Okay, so bounded multipliers allow lemma 8, which bounds the subgradient norm at the solution using the step size. Then lemma 9 uses this, combined with the local KL assumption, to show that the function value converges to the optimal value $.
Yes. Lemma 9 establishes the rate of convergence for a GitCK. It decays exponentially if theta cia 212, the PL case, or sublinearly like k of theta 1 in 12.
And Theorem 5 puts it all together. It says algorithm 1 terminates in a finite number of outer iterations, let's say k theta.
Right. The termination criterion checks if a certain measure of stationarity, involving gradients, multipliers, and step size, is below a threshold, tau tau. Theorem 5 guarantees this condition will be met.
And the number of iterations k theta needed depends strongly on the KL exponent theta. Formula 35 shows it grows like paudo or taudo depending on the theta.
Essentially, if theta is close to 1 weak KL property, the theta becomes very large. If theta 12-2, strong PL-like property, the dependency on tau is much milder logarithmic dependence hidden in the constants.
So the efficiency of the inner SCP solver is fundamentally tied to the geometric regularity of the inner problem as measured by theta.
All right, now we have the SCP method, algorithm 1, as a tool to approximately solve the inner maximization by minimizing Fy. Let's see how algorithm 2, the inexact proximal gradient IPG method, uses it to solve the overall outer minimization, Fx plus Px.
We established it's potentially non-smooth because Px is only Holder smooth, Theorem 1. And evaluating Glauber's gradient x exactly requires solving the inner problem exactly, which is too costly, hence IPG.
Exactly. IPG is designed to work with inexact information about 5x and nth gradient. The key idea is to use an approximation based on the output of the SCP subroutine.
The algorithm operates locally within a neighborhood BSK defined by some radius $. Theorem 1 gave us the local Holder smoothness constant and exponent to fan for nominal values of that $.
Right. Using this local Holder property, the authors derive an approximate quadratic model for around the current iterate $6. This is sketched leading up to equation 39.
The bound 39 essentially says that if 6 gal is not yet close to being stationary, then E is upper bounded by a function involving a linear term using an inexact gradient, a quadratic proximal term, and the simple function phi.
The crucial part is the inexact gradient. Instead of using the true unknown off the xk, they use Neblax fxkyk, where f to k is the approximate solution to the inner problem found at the previous iteration.
Okay, let's walk through algorithm 2. Line 3 sets up parameters for iteration k, decreasing error tolerances deltac 1k plus 1k plus 1 tac. It also defines an adaptive smoothness parameter.
Our fate acts like an adaptive estimate of the local Lipschitz constant for the approximate quadratic model. It incorporates the known smoothness off to k and the Holder parameters derived from a theta.
Then line 4 is the core IPG step, computing the next iterate next k plus 1 pale. It's found by minimizing the approximate quadratic model within the local ball, BXK rank.
Specifically, 6k plus 1, xk2 plus psk wrangle plus pxk, our fate, xk2 plus pxk.
So we use the gradient information alpha class, sxxk, yk computed, Using the previous inner solution, y-ticklets, we add the quadratic term and the simple function t-eklar. And we solve this proximal subproblem, but restricted to the ball bxk to ensure the Holder approximation is valid.
Right. This subproblem involves the simple function p, so it's typically solved using the proximal operator of p.
Okay, that gives us xk plus 1, 1. Now we need the next approximate inner solution, 1k plus 1 on, to use in the next iteration's gradient calculation. That's line 5.
Line 5 calls algorithm 1, SCP, to approximately solve the inner maximization problem at the new point xk plus 1, 1. Specifically, it solves 101 Euler subject to 2 Teller's 1.
It starts the SCP solver from the previous inner solution, UKL as a warm start.
And crucially, it sets the termination tolerance Toller for SCP dynamically. Toller is set based on the outer iteration count k and the overall target accuracy epsilon dollars. It needs to decrease as k increases.
So the inner problem is solved more accurately as the outer algorithm progresses.
Yes, that's essential for convergence. The inexactness needs to diminish over time.
Just like in the SCP analysis, we need bounded multipliers here too. Lemma 2 confirms this.
Yes, Lemma 2 provides a uniform bound A5 for the L1 norm of the Lagrange multipliers lambda generated within all the inner SCP calls across all outer iterations k. This bound depends on GXSY, but it's uniform. This again relies ultimately on MFCQ.
All right, we have the two nested algorithms, IPG calling SCP. Now for the main theoretical payoff, the complexity results. How fast does this whole procedure converge? Lemma 10 seems to be the engine driving these results.
Lemma 10 is critical. It quantifies precisely how good the inexact inner solution heel computed by SCP at outer iteration actually is, particularly when the outer iterates is still far from being epsilon stationary.
What does it guarantee?
It guarantees several things. First, the optimality gap for the inner problem at Sexel is small. Epsil is bounded by terms related to the tolerances, SL in the outer stationarity gap epsilon sigma.
So the Euler found by SCP yields a function value very close to the true maximum dollars.
Second, it guarantees that Euler is physically close to the true set of maximizers. Euler's is also small, bounded in terms of Geller and Therton-Valor.
And third, and perhaps most importantly, it bounds the error in the gradient approximation used by IPG.
Yes, equation 73. It shows that the norm of the difference between the true gradient F-level and the inexact gradient F-level is small. Specifically, it scales roughly like to 0. So as the inner tolerance goes to 0, the inexact gradient becomes a very good approximation of the true gradient. This justifies the whole IPG approach.
Precisely. Lemma 10 confirms that the inexactness introduced by using SCP as a subroutine is controllable and diminishes sufficiently fast.
Okay, with Lemma 10 establishing the validity of the inexact step, Theorem 6 gives the overall iteration complexity bound. This is the number of outer IPG iterations, calls to SCP, needed to find an epsilon R stationary point. Right. The formula for K looks complicated, but the dominant term involves epsilon raised to a negative power.
Let's focus on that exponent. Epsilon back sigma theta of 1.
So the convergence rate is determined by the maximum of two exponents related to the KL parameters. The first is $1 theta 1 coming from the Holder smoothness of error. The second is sigma theta coming from the localization definition in the KL assumption.
Let's revisit the impact of theta. If a theta is equal to 2, PL case, then 1 sigma 1, 2 of 2. If sigma is small, say sigma doll, then the complexity is dollar as 2. That's similar to standard gradient descent for smooth convex problems.
But if theta gets closer to 1, say theta 0.1 1, then 1.1 and others $10, the complexity becomes epsilon 10 ignoring sigma for simplicity. That's drastically slower convergence.
And the sigma term acts as a potential floor. If sigma theta is larger than 1, though theta 1, it dominates. The sigma parameter measures how quickly the local region shrinks.
So the iteration complexity is fundamentally limited by how nice the function is locally, measured by theta, and how restrictive the localization needs to be, measured by sigma.
Okay, that's the number of outer iterations. What about the total computational cost? That's Theorem 7, the first-order oracle FO exolexity. While epsilon measures the total number of times we need to compute the gradient de noble FV, both N-Black-Civil and F-A, which is usually the most expensive operation. It's roughly times the number of gradient calls needed per SCP solve.
And the analysis shows that the number of SCP iterations per call also depends on theta and the tolerances.
Right. When you combine the outer complexity with the inner complexity from Theorem 5, appropriately scaled to the tolerances, you get the overall FO complexity telon.
The paper gives the results for 2 cases based on theta. Let's look at those.
Case 1. Theta telon abundant 12.2. PL-like condition locally. The total FO complexity is $all 2 max 1. Still polynomial in $1 and Segna. Case 2 in 12, weaker KL condition. The complexity becomes significantly worse. Fracta theta, fracta theta, frax of 1 theta, frac of 1 theta, fixilon.
That exponent on epsilon looks intimidating. Let's try to understand its behavior. The term 2 theta plus 1 theta combines the cost contributions from both the inner and outer loop's dependence on theta. As theta to foletta, this exponent blows up very quickly.
So summarizing the complexity, the number of outer iterations k theta plus 2 letta, the total gradient evaluations max sigma theta, the total gradient evaluations scales like tilde theta plus 1 theta, where tilde hides logarithmic factors.
It clearly shows the price of non-convexity and non-concavity, even under the KL assumption. The closer theta is to 1 lie, the harder the problem becomes computationally.
Okay, after that heavy dose of theory and complexity analysis, the paper provides some preliminary numerical results to show the algorithm actually works in practice.
Yes. They tested on a specific constrained minimax problem defined in 43 and 44.
The objective involves the squared norm of a Hadamard product. The y plus x, odit y plus bx, that looks highly coupled and nonlinear.
It is. A and B are matrices. The outer objective also includes L2 regularization on X, and L1 penalty sit-down, and a constraint forcing X into a ball.
And the inner constraints, 16yy of 4, are sums of exponentials, like AE $10. Also quite nonlinear, but smooth is required.
So it seems like a reasonable test case that fits the paper's assumptions. Non-convex, non-concave F, simple P, simple Q, implicitly handled, and smooth nonlinear C.
They run algorithm 2, initializing at the origin, setting parameters like theta 5, assuming the faster PL-like case locally, and sigma dollars in 1 cents, aiming for an accuracy epsilon 10-2.
They run it for 2,500 iterations on problems of varying dimensions, N1, N2.
Table 1 shows the results. What are the key takeaways?
First, look at the objective values. The initial value is around 0.5 to 1.5. The final approximate value computed by the algorithm is drastically lower, ranging from Mannequin 65 down to Eclipse 590 for the largest problem size.
So the algorithm is clearly achieving significant optimization, finding much better solutions than the starting point.
Definitely. But the more subtle and perhaps more important validation comes from comparing the approximate final value hapsilon with the actual final value haxilon.
How do they get the actual value?
They take the final outer iterate sexilon found by algorithm 2 and then use a separate high-precision solver, global search in MATLAB, to exactly solve the inner maximization problem hapsilon y to find the true epsilon plus p epsilon plus p epsilon plus p epsilon is just quas epsilon plus p epsilon, using the final inexact inner solution lepsilon produced by the last call to the SCP subroutine within algorithm 2. Right. And the table shows these two values, SAP, Salon, and Hattel, are incredibly close across all problem sizes. They differ only by about $10 or less.
That's remarkable. It means the final inexact inner solution, yepsilon, found by the SCP subroutine was practically optimal for the inner problem at its epsilon.
Exactly. It provides strong numerical evidence that the inexact approach works. The dynamically terminated SCP subroutine delivered an inner solution good enough for the outer IPG method to converge to a point where the overall objective value is essentially correct.
It validates the core idea that you don't need to solve the inner problem perfectly at each step, and it supports the theoretical analysis like Lemma 10, which bounded the impact of this inexactness. #tag outro. So reflecting on this whole deep dive, what we've really seen is, well, a masterclass in navigating the complexities of modern optimization theory.
Absolutely. The authors took on a really challenging class of problems, these constrained non-convex, non-concave minimax scenarios, which appear in many areas like robust optimization and adversarial ML.
And they successfully extended convergence guarantees to this class by designing this sophisticated nested algorithmic framework, IPG wrapping around SCP.
But the core achievement, I think, was fundamentally mathematical. The clever use of the lifted problem formulation.
Right. Introducing that auxiliary variable z to simplify the constraints.
And then imposing the local Kurdyka-Łojasiewicz condition on that lifted problem. That was the key enabler.
It allowed them to derive those crucial structural properties, like the local Holder smoothness of the value function, $5, which you probably couldn't get otherwise.
And the payoff wasn't just qualitative convergence, but quantitative bounds. Those complexity results, showing the explicit dependence on the KL exponent theta and the locality parameter sigma terals, give practitioners a much clearer picture of the computational trade-offs involved.
It maps out the fundamental limits, based on the problem's inherent geometry.
Precisely.
So as we wrap up, we always like to leave you, the listener, with a provocative thought. And one that strikes me here comes from that core mathematical trick, the lifting.
The equivalence they established. Maxi x, y, z. Yeah.
Maxi z-bar.
Yeah.
It suggests that sometimes the path to solving a complex problem involves, perhaps counterintuitively, adding more complexity, like the auxiliary variable z and the surrogate constraint.
But doing so in a way that the new higher dimensional structure is actually mathematically simpler or better behaved, allowing for rigorous analysis and convergence guarantees.
So the question is, if this kind of constructive convolution, adding structure to simplify analysis, works for these complex non-convex constraints, what other notoriously hard problems in optimization or maybe control theory or other fields might become tractable if we're willing to think creatively about lifting them into a different space? Where else could we introduce auxiliary variables to unlock hidden mathematical structure?
That's a powerful question. It challenges the standard intuition to always simplify. Perhaps sometimes the way forward is through strategic complication. The future of tackling these really hard non-convex problems might involve embracing, rather than just fighting, structural complexity.
Definitely something to ponder. Thank you for joining us for this incredibly detailed deep dive. We hope you found it valuable. We'll see you next time.